Okay, come to order. Sorry, I have a microphone. Welcome to this wonderful location in San Francisco. So many old friends here, but also many new faces. So really great for the people who come here. We've got a kind of opening triple act. I think I am to inform you of different things about the plenary, and I think I hand over at this point to Angela. So Angela, tell us about the plenary.
We usually make Ewan do this part, the housekeeping, but we thought we'd give him a break this time. How do I advance? Is this how I advance? Someone? No? Anybody can tell me how to advance the slides? Tech support. This is a microphone. Okay. Maybe I'll just say next, and then you can do that. All right, Ewan is done. Next slide. It's not done, but, you know. Next slide, please. What button do I push? There's lots of buttons. 3? Push number 3. Green. There's nothing green on this. This is a television remote control. It's probably right in front of me, too.
Here comes an official helper.
Good. Sabotaging. Okay, well, let me see if I can remember what is on my slides while we're doing this. So, number 1, welcome. Thank you for being here. We want everyone to stay safe and healthy, so we have some health and safety recommendations on our website you can check out. We also have masks and COVID tests at the registration desk, should you like to use one, and please respect the decisions of your colleagues to mask or not. What else is on there? I think, what's that? You know what I should do? I'll just get my computer. Yes, okay, Wi-Fi. You all have little table tents telling you the Wi-Fi information. Oh, and there's the last slide from the last thing I said. Next slide. Next slide. Okay, good, thank you. Next slide. Attendee mobile app. If you have not already downloaded it, this is your one-stop shop for GA4GH. Go to your app store and search for Attendee Mobile, and then search for GA4GH in there, and you'll have meeting agenda, everything you need. Next slide. Okay. For those of you that are new to GA4GH meetings, we use Slido for questions and answers. We also have mics in the room, but we're going to encourage everyone to use Slido. This allows virtual participants to engage kind of at the same level as everybody in the room, and we will do a little test here. If you can navigate to sly.do on your web browser or download the app, and then once you're in there, search for GA4GH, and then you will be presented with the question, what are you most excited about 11th Plenary? And there are lots and lots of things to be excited about, so expect to see lots of answers. And we'll go to the next slide, where we will be able to watch the magic in real time as you answer this question on sly.do. Maybe. Are you answering it? Ewan, are you glad that you didn't have to do this job? Yeah. All right, great, there we are. So meeting new people, hugging Melanie. The Anna robots are awesome. We're so happy to finally have them. They got lost on the way to Spain last year. meeting new people, new connections. This is what is so great about GA4GH, is this incredible community, people coming from all over the world in different contexts. So it looks like we all understand how to use Slido. If anyone has a question, ask it on one of the Slack channels. And again, we have mics in the room, but if you could use Slido, that would be helpful. Lunch, yeah, it was great. Next slide. Next slide. There we go. All right, we have a brand new Code of Ethics and Community Conduct, which was put for open comment a few months ago. You may have seen it. It is now released in its final version, and the point of it is really to make everybody in this room and in our whole community feel safe and included. These are some of the sort of top priorities for how to behave. We all know how to behave, but a reminder. Behaviors that would not be tolerated. If you witness or experience anything that you would like to report, there are ways to do it. It's all on our website, and emails and whatnot are there. And then if you advance to the next slide, we also have now a Safe GA4GH committee. This is the community of people that you can go to if you have a concern. You can email any one of us directly, or you can email conduct@ga4gh.org. Next slide. I am going to pass it over to David Glazer for the third part of this, but before I do that, I just want to thank him. He is here as the chair of the program committee for this meeting and has put together an incredible agenda along with all those folks on the slide, so thank you, David.
Thanks, Angela. And the green button is verbal?
It's verbal button.
Okay, I got that. Next slide, please. And I want to thank Angela and everyone else who kept their promise when they said that chairing the program committee meant they would do most of the work and I'd stand up here and say thank you. So appreciate that. So I wanted to I was trying to think, what can I say about San Francisco? I just said, let me put down 5 of my favorite things in the area. So if any of you happen to have a little bit of extra time, this is my short list of a handful of things I'd recommend. The Ferry Building is just down the hill, great place, lots of fun restaurants and shops. Alcatraz, or anything that gets you on the water. This is the Bay Area, and find an excuse to get on the water. You just see the city, see what's around better. Muir Woods is a little bit north of here, and it's it's the most accessible place to really find yourself in the redwoods, and it's impressive and easy to get to. Plan ahead if you do that. And then a personal favorite, Dandelion Chocolate Factory does a great factory tour. They do great bean-to-bar chocolate. It's just that's my local chocolate. So if you're interested in chocolate, look them up. Slight, reminder and warning is that we all brought smoke with us. Apparently, that's the air sensor at my house there, that's part of the network of air sensors. So just pay attention to the air. The same masks that keep viruses out do at least as good a job of keeping particles out, which is good. So we're all prepared for that. Next slide, please. I had a chance a couple weeks ago to spend a week at the bottom of the Grand Canyon with my son, and it got me just thinking about time. And a book I had read not long ago that really just put some context in place, just really backed off and said, hey, everything the pace at which we live our lives is part of a much longer picture. Next slide. For example, one of the things that they point out when you're in the Grand Canyon is you're looking at all these layers of rocks, and they say, well, this rock is 1.8 billion years old, the Vishnu schist, and then right above that, there's some rock that's 500 or 600 million years old, and there's nothing in between. And that's called the great unconformity, and that's the kind of scale that geologists think about. And you can see the layers where there was no life. The bottom layers are before any life existed. And then you've got the layers where bacteria existed and DNA existed for the first time. And then you get the layers of what we think of as fossils beyond that context. And it was the connection, for some reason, next slide, please, I was thinking about that sort of the deep time, how do we get here? And with that, I want to acknowledge that there were people here before we were here, before the buildings in the city were here. And we are on the unceded territory of the Ramaytush Ohlone, who were the original people who lived here on the San Francisco Peninsula. Next slide. A little bit more about history and time, and I was thinking back to when Ewan hosted us at the Royal Society, and the motto of the Royal Society is basically, back in 1600 was don't believe, it was question authority. It was, the Latin version of question authority. And it was it's a reasonable, slight stretch, slight oversimplification to say that moment in time and that attitude marked the beginning of the journey we are all on as scientists and discoverers of how the world works in a structured way. And that started back around 1660. Thank you. Next slide. Oh, I can do that now. Wow, look at that. It's not green, by the way, but it is an arrow, which I can figure out. So getting a little closer to right now, where we are right now was originally the site of Mark Hopkins. He was one of the he made money on the first internet, the railroads. He was one of the railroad barons, and they built their houses on the high spots in San Francisco. And so his mansion was here, which then became an art museum and then burned down in the fire after the earthquake in 1906. And then they built this hotel on this spot, which opened in 1926. So that's where we are now. And the last thing, and I wasn't going to do this, but then Angela kind of reminded me of it yesterday. So the last piece of San Francisco that I wanted to just say, hey, remember where we are. And this is as we welcome the 500 people who are here virtually and in person from over 40 countries. For those of you who are here, just want to remind you of another piece of local color, that this is where the Grateful Dead started. And right there on the map, you can see less than 2 miles from here is where their final concert was. That was a picture from my seats on the right there. That's where I got this shirt. So anyway, welcome to San Francisco. Thank you all. I'm looking forward to the day.
So one more thing here. So I get my devices. Just to say that GA4GH has been growing up over the last couple of decades, and we'll have more of that over this plenary because it's 10 years worth of GA4GH. We have decided on more structured ways of doing the change in leadership. And just over the summer, I stepped away from, or announced to the board that I was going to step away from being chair. And on the 1st of January, I became chair emeritus, a new role in GA4GH. So I step away from being chair. And the very wonderful Heidi Ream was nominated and accepted to becoming chair of GA4GH. So on the 1st of January, there'll be a new chair of GA4GH under Heidi. We're going to discuss this. Yeah. So just two kind of things from my perspective of this, just for people to understand my motivation. It's been a long time that I've been doing this job, and it's worth, I do many jobs. And I needed to transition, I think, for myself, but also for the organization. I've taken it as far as I can. I'm extremely proud of how GA4GH has grown up. I feel like I took GA4GH over when it was a sort of young teenager, and it's now a 20-year-old adult. So Heidi, you get to really, find that career plan for GA4GH and everything else. I'm very proud as well that we have really embraced the global nature of GA4GH. That is a work in progress. I don't think we're not as global as we could be or as we should be, but we are a lot more global than we were 10 years ago. And it's wonderful to see so many people in person here. The second thing to say, just to make it really explicit, is that myself stepping away from being chair does not change the enthusiasm of EMBL-EBI for its engagement with GA4GH. So I'm Deputy Director General of AnVIL, the European Molecular Biology Laboratory. I'm also Director of AnVIL EBI. And as Director of AnVIL EBI, we are still 100% committed to GA4GH. We have two roles there. So one role is that we're a host site, meaning that we house some of the secretariat that makes this organization work, and will continue to be play that role. And we're also deeply involved in a number of the projects at GA4GH. In particular, there are many colleagues here across AnVIL EBI who have come here and engaged with this. And myself, and perhaps more importantly, the Associate Director of Services, Joe McIntyre, we are both all in on GA4GH. And then I just want a sort of final call to arms. I'm still going to stay engaged in GA4GH. I feel like the last piece of business that I still want to achieve is really seeing these standards implemented in the real world. I have a particular passion of making this work for Europe in all of its configurations. Europe's been a leader in the way genomic data has been collected and distributed and powers research. Your default human, if you study them, are either a Brit or a Finn or maybe a Dane. And that goes as a tribute to the organization in those countries that has allowed both the generation of the data sets and the linkage to healthcare records to achieve that. There's some wonderful Spaniards, French, Germans, Swiss, all sorts to link up as well in the future. And I really would like, for my European colleagues, I'd like us to implement these standards and stay right at the forefront of genomics. So that is my personal commitment for GA4GH, and for my European colleagues, expect my advocacy to get even stronger inside this. So you'll hear more about this on Friday, where I get to, Heidi gets to interview me first, and then I get to interview Heidi, and that will be how we close the session for GA4GH. So we now go on to, these we're going to have a lot more schmaltz, I'm sure. These are some of the pictures in my phone and other phones of me in GA4GH action, or seeing people. There's a bit of Toronto and Montreal. That is Barcelona drinking cava on the bottom right. And this is me in California. I was, for the people who came for GA4GH Connect this year, I was a tour guide around the palaces of London in all their different configurations. So that's me just explaining some piece of obscure English history. And that, I believe, top right is in, no, the bottom right is London, top right is somewhere else. Is it Boston? No, Orlando? Anyway, I have visited many places for GA4GH. And it's been great fun, not only the kind of technical delivery side and just making this thing work, but of course meeting so many people and seeing so many people come to this organization, which has been wonderful. So we're going to thank, we are funded in a variety of ways, but in particular, I'd like to call out the second layer here, the core funders, from CIHR in Canada and Genome Canada, UKRI in the form of the Medical Research Council, NIHR, that's the research arm of the Department of Health in the UK, the NIH in America, and the Wellcome Trust. And the funders are the people who allow the Secretariat to operate and deliver these meetings in the work stream so wonderfully. They're hosted by the four host sites, which you can see at the top. And we're very, very also happy about the corporate sponsorship that we've got listed at the bottom. If you're a corporate member, if you come from a company and you want to see your company down at the bottom, please do approach Peter with your checkbook. With that, I think we're done, and we go on to Peter. Yep. Peter.
Big thank you for you.
David Glazer, leaving his identity behind. I'll bring it to you. I think in that big round of applause, I wasn't sure whether it was entirely for Heidi coming in, but I assume in there was a huge thank you for Ewan at the end of this 6-7 years. We'll say more of that as the week goes on, but I would probably just like to say, Ewan, not only have you done what you set out to achieve, you've been a great partner for me to work with over these last few years. So, big round of applause for Ewan. I don't think I'm actually going to take the whole half hour, but we'll see. So I've had the privilege of being with GA4GH from the very beginning, so I can speak of this. We synthesized a little bit of that into one. It works.
This
Okay,
year
I can
marks a
make the
decade of GA4GH, and what a decade it's been. Let's hit replay and see what we've accomplished together. Back in 2013, the cost of a single genome had plummeted to under $10,000 down from $10 million just a few years earlier. Led by David Altshuler, soon to be the first GA4GH chair, our forward-thinking founders realized that the coming deluge of new data would never reach full potential unless we figured out how to work together. 73 partners signed a public letter of intent to form an alliance and address the need for genomic data sharing. We kicked things off with our first 4 working groups: data, clinical, security, and regulatory and ethics. In 2014, we held our first 2 plenary meetings ever in London, UK, and San Diego, US, and published our landmark Framework for Responsible Sharing of Genomic and Health-Related Data. Based on the human right to benefit from scientific advancement, the framework has underpinned everything GA4GH has achieved since. Also this year, our 3 flagship demonstration projects came together to highlight the power of data sharing: Matchmaker Exchange, BRCA Challenge, and the Beacon Project. Today, each has become a major player in the genomics and health world. MIT Technology Review included GA4GH on its list of 10 breakthrough technologies for 2015, the year we next met in Leiden, Netherlands, where we maxed out the Wi-Fi at Plenary and walked around inside a giant human body. Led by our second chair, Tom Hudson, we wrote a perspective article calling for a federated ecosystem to share genomic and clinical data. Science published the article in 2016. Together again for Plenary in Vancouver, Canada, we launched a group that convenes national genomics initiatives to compare notes on implementing genomic medicine at scale. Our third chair, Ewan Birney, called on each of us to imagine an even more productive and effective organization. At a working meeting on the Wellcome Genome campus in 2017, we came up with the idea for driver projects, collaborating closely with work streams, ensuring users had a voice in the standards development process from the very start. The first 15 driver projects joined us that year, and the 8 work streams we've come to know and love launched at 5th Plenary in Orlando, US. That year also marked the start of a new 5-year strategic plan, GA4GH Connect. The first tools produced under GA4GH Connect debuted in 2018 at our plenary in Basel, Switzerland, where Ewan congratulated the product teams with champagne and Swiss chocolate. In 2019, we welcomed another 7 driver projects, extending our domain expertise and our geographic reach by 31 countries. We gathered in Boston, US for 7th Plenary, and by the end of the year released 12 new products. And then the COVID-19 pandemic put the world on pause. But rather than mark a dark era for GA4GH, 2020 forced the world to acknowledge the true value of data sharing, and our community pivoted, applying its knowledge of sharing human genomic data to sharing pathogen data. Our first fully virtual plenary attracted the largest and most diverse audience yet. We showed connection demos of GA4GH standards solving real-world scientific problems by allowing researchers to analyze data distributed around the globe. In 2021, more than 200 of us worked together on a special issue of the new open access journal Cell Genomics. There, and at our virtual 9th plenary, we discussed how GA4GH and our products could enable responsible data sharing in genomics and health. In 2022, for the first time in 3 years, we saw each other in person, meeting in Montreal, Canada, and then again in Barcelona, Spain. Which brings us to today. 44 GA4GH products now form the foundation for responsible genomic data sharing and use. We welcome a new cohort of driver projects as we celebrate 10 years of unlocking the power of genomic data to benefit human health. To our active contributors, thank you for all of your work and your commitment along the way. You are GA4GH. You made this happen. And to those of you just getting started, we're so happy you're here, and we can't wait to see what we can achieve together. Here's to the next decade.
So I will say one of the things that's really differentiated GA4GH over the years is our communications and the sophistication of those communications. And most of that has been initiated, if not all of it delivered. Angela has put together both from her own contribution and then the team that she's assembled. It's one of the things that makes us a little bit different from many of the organizations we work with. So I will now kind of give a little bit more of my perspective on that. There were 73 partners who signed that letter of intent. It's a bit of a mad scramble because we started actually in January 28th, 2013, and by the middle of that year we launched the white paper. The world has changed a lot since that white paper was written. I read it again this morning. Some of it was very predictive, others, it's not quite the direction we went, but it made a very clear public statement of what we intended. And I think, Angela, the video is just taking you through those plenaries, but there was this startup phase, this pre-launch, with a handful of people doing it purely on trust and with not much money. Then there was that building momentum phase that Ewan described as when he came in. That was our pre-teen era. And Connect is when it really started to shape. And you could see it in everything, from our funding to our organization to our focus on product delivery. Connect was very much about making our standards be ready for purpose and be used in real world. In any of these organizations, leadership is an essential quality. We were very lucky in the beginning. There were 8 people who wrote that original white paper or brought it together, hosted the meeting. We added a few more people to that original transitional steering committee. Was it just one of them still? 2 of them? 2 of them and me. 3 of us still involved in GA4GH leadership today. We also managed to convene a really senior strategic advisory board. We told them we didn't want to make it a scientific advisory board. We wanted a strategic advice because what we were doing is not doing the science, but enabling it at scale. And as the video showed, we're now just on our 3rd chair. And Ewan, fortunately, I think we made it a condition of when he made the condition. I'll do it, but you have to get ready. I'm going to be disruptive. And he was, and it's been really productive for us. The flip side, it was like, please don't go to industry, because we lost the first 2 chairs because they went to industry and felt it wouldn't be the right way to lead a global organization like GA4GH. We had 3 demonstration projects, the 3 that the video showed. We had 4 working groups, and today in 2023, 8 work streams, 6 technical, 2 foundational, 28 driver projects. I guess okay. It's not 30, it's 28. Breaking news. But clearly this last phase, since Ewan took over in 2017, has really been when we grew up to the stage we're at today. But we never want it to be a traditional standards organization, because that would mean we'd take years to get things, and once they were done, they'd be locked in, and we wouldn't be changing. And our sense was that the nature of genomics and the combination of genomics and data science said we had to be more flexible, more adaptable, we had to move quickly. And although we would push as hard as we could for rigorous interoperable standards, we also had to recognize that we had to move quickly and we had to make them work in the real world. So a big emphasis not just on developing the products, but making sure they're used and used appropriately. 2020 was a gap analysis that Heidi and Andrew Morris led. It came up with these 3 new strategic imperatives. And when we checked that just this year, it was that the strategic imperatives are still right. Focus on interoperability and alignment between the standards, make the standards easier to implement, and get closer to healthcare. The strategic refresh said, yes, they're still important. You need to do some more concrete things to get us there. Our community today is made up of 1 strategic partner, hopefully soon to be 2 strategic partners, 28 driver projects, not 30 or 24, 500 plus organizational members. Assigned experts is a new concept. It's for those funders and those organizations that cannot send money to our host institutes to employ GA4GH staff, but can dedicate resources and people in their organization, or they can fund them locally. We've got a handful of those assigned experts today. They spend more than 30% of their time on GA4GH, some 100%. And then we've got hundreds, probably 450 plus, active individual contributors, and more like 4,000 people who sometimes open our emails and our newsletters. We've got, one of the things we got stronger about is defining the need up front. In the first phase, we used to, somebody had a great idea, put a lot of enthusiasm in it, we got going. And then we could find out 18 months later that nobody knew quite who was going to use it for what purpose. So we got more deliberate up front in the study groups. We saw 3 of them today, two today, saying this is what we think is important. We're validating before we start that this is something we really should get going with. So a more deliberate onboarding, create the standards of policies, and then more emphasis on implementing. Not that we're going to do individual implementations for organizations, but better reference implementations, better documentation, better guidelines, so that the standards can be more easily and readily adapted. 2 things in the middle, the National Initiatives Forum, which has been there all the way back to Vancouver, but also increasingly, and I think we just saw the birth of a new one this morning, communities of interest, driver projects and others coming together and saying, we've got a cancer community, we have an infectious disease community, we have a rare disease community, and I know the neuroscience community was meeting this morning to see if they've reached that point of traction. Staff has grown over time, staff has come and gone. So you can see why I rely so very, very heavily on Justina and Angela, because we've kind of been in it from the beginning, in my case from before the beginning. We've had 17 staff leave us over this time. The really great news for us is that 11 of those 17 have stayed connected with us one way or another. About 4 or 5 maybe are in the room now, right now. They've become driver project champions, they've become work stream chairs. So although I typically give them enormous grief when they leave, or to the organization that's hired them, and there are 2 main culprits. But the great news is they've stayed close to us, they've stayed engaged, they've been part of building this remarkable community, and they've spent their time and energy continuing it. They've spread the GA4GH world. With the support of the major funders that Ewan described, the core funders, we've been able to scale the organization across the 4 host institutes. So, and I hope we've caught everybody who's been and gone, and I certainly hope we've got everybody here except our next hire who starts next week. So, this is a staff complement today, but the 20 or so people you see on this slide, all they really do, in essence, is mobilize the 450 contributors, because the leverage effect, this group could not do a fraction of what GA4GH is tasked with doing. Actually, in the beginning, it was 3 host institutes, Broad, OICR, Sanger, and they self-funded it. There was no external funding. It was the presidents of those 3 organizations saying, this is big, it's important, the world's going to change. If we don't be part of that change, we could get left behind by it, or it will be really messy and noisy, and we won't realize the potential. So let's get going. And that really is 2012. Today, there are 4 host institutes, AnVIL EBI, as Ewan described, added to that set of host institutes. You can see there's space for a couple more. We're open to more suggestions. bring your checkbook with you when you become a host institution. No. But more importantly, we've managed to get significant, secure, and in most cases long-term funding from within the US, the UK, and Canada. They fund money primarily through the host institute in that country, but certainly in the case of NIH and Wellcome, they're able to support work outside their home country, and that's critically important to us. The community is big. So, from 73 partners signing a letter of intent. Letter of intent pretty much just said, we're going to use our best efforts to do this really noble thing that we've read about, but we're not bound by anything. That really was a very light letter of intent. That's how we got 73 signatures. But today, most of those signatures have turned into action, not all of them, and the community has grown with some very, very significant, tangible contributions. Oh, I think I'll go back one. Brad, do you think? But also the scale of genomes. In 2013, when we were talking about this, we were talking about tens of thousands of whole genomes at best. The 1,000 Genome Project, the ICGC original project, I think we were less than 100,000 genomes globally. Today, the new driver projects alone, well, the new driver project community, as of today, will represent somewhere north of 4 million genomes if we've got our math and our questions right. I think we might have asked different questions. But in terms of what they intend to do, just the 28 driver projects will be 4 million genomes or more. When we started, I went through the white paper. There was no mention of the word federation. We did talk about this new thing called cloud computing, which might actually be good, and particularly if NIH would lift its embargo on cloud-based platforms, but we didn't mention federation. So over those 10 years, the world has changed in terms of scale, in terms of approaches. Data science has kept up with those changes. It's rarely been the limiting step. The world over the last 3 years has become a world of Zoom and Microsoft Teams and other ways of communicating and meeting virtually. We were actually using Zoom before anybody knew what Zoom meant, other than go really fast. And so we had a lead in the Zoom world. It turns out we're not the only global genomics group. There are lots of other people in this space. Of course, getting to make the slide, we put GA4GH right in the middle of this. And we also managed to drop the Science Council out of the World Health Organization from things. But these are the other groups that we would typically work with. And the message to these groups is that GA4GH, and some of them are in the room, the message from GA4GH to them and usually back to us is we want to work together. We've got different roles, different mandates, different focus in different parts of the world, but collectively we make up a global genomics community, and we intend to work together for the benefit of humans around the planet. When we started that meeting in New York City in 2013, we had 8 countries represented. Our driver projects, as of today, are active in 113 countries. We've still got more to do, and I would say sometimes it's a very light touch. The driver project might be active, doesn't mean we are. These are the 10 new driver projects, and I will not go through all, but you can see they've all got great logos. Some of them have got really memorable acronyms, others don't. But the important thing is they expand our geographic scope, they extend our clinical focus, they extend the different approaches to the way we handle and leverage genomes. So we had them present this morning to our steering committee, most of them. 3 of them, we're still in that final stage of clarifying expectations, responsibilities, so 3 of them are pending. But this community added to the original community. We had 2 transition from their old driver project to one of these new ones. That will be the case with NIH, Biodata Catalyst, and the Biomedical Research Hub, were transitions from previous driver projects. 4 of the original driver projects have come to the end of their mandate and have so dropped off. The rest continued, and that's how we end up with a new number of 28. There are the 28 in total. It's an incredibly impressive group, organizing them in a matrix between 8 work streams, 450 contributors, and 28 driver projects is what that staff group you saw will spend a ton of its time on, particularly 2 or 3 of us. And that, from me, I'll just finish with a personal note. So we couldn't have got where we are today without a combination of leadership, of funding, of resourcing, of volunteer. We tend not to use the volunteer phrase too much, but active contributors to GA4GH who are giving of their time, their energy, and their expertise. And without that combination of core funding, dedicated staff, leadership, and a community that is focused on being collaborative and making a difference, none of this would have happened. So people often say to us, you know, GA4GH has done really well. It's not this GA4GH that's done really well, it's this GA4GH. And one of the great things about meeting today is seeing not only have we got many familiar faces who've been with us from the very beginning, we've also got a lot of new people, fresh ideas, fresh thinking, and that's what we constantly need to keep this thing moving forward over the next. Seems there were discussions with, so we're going to Slido. It seems, and in addition to just being able to post your question, if you also see a really great question that will be easy for me to answer, you can upvote it so it comes to the top of the screen. If you see a difficult question, just leave it there. I think the discussions with RDA were really at the London Connect meeting rather than the Barcelona meeting, but we certainly do see the opportunity to work more collaboratively with RDA. They've got this very broad focus, and it's all about research data. We've got this narrow focus, and it's about research into healthcare, so we've got slightly different mandates. But we certainly had the joint session at the opening of Connect. GA4GH leadership made up of 2 chairs only? No. So GA4GH leadership is 2 main bodies. One is the GA4GH Inc. board, which has 9 members on it, and the other is a GA4GH steering committee, which is 1 representative of each driver project and both co-chairs of the work stream. So that's probably over 60 individuals today. So the 2 leadership bodies of GA4GH, the Alliance is led by the steering committee, the legal entity is by the board. There is a chair, and there were 2 vice chairs. Now we have a chair, a vice chair, Catherine North, and a chair emeritus. And over the time as that, well, in fact, we've still got you and Bernie and 2 vice chairs. As of January 1st, they switch and become Heidi, Ewan, Catherine. And then over time, as Ewan steps down from chair emeritus, there will be a new vice chair elected. So that's the chair situation. And the chairs of the GA4GH Alliance are also the chair and vice chairs of the board of the legal entity. Yeah. The next quantum. I don't think it will be quantum for a start, but I think the real issue in sharing data that we've learned in the last 10 years is technology, data science has almost never been the rate limiting step. The rate limiting step is almost always humans and legal systems and IP and barriers from communities. So I think that sense of what is the quantum advance will be seeing some really strong use cases demonstrate to others, other countries, other projects, other funders, this fundamental shift. What I hope happens is what we've said for a long while, that we can start secondary use of healthcare genomes, and those massive healthcare budgets around the planet can fund the generation of the genomes that will be well annotated and described clinically, phenotypically, and that research dollars, research grants can be spent not on generating genomes, but on actually analyzing and making sense of those. As proud as 1 or 2 accomplishments. I think from a GA4GH point, well, at a personal level, I'm incredibly proud of the staff that are with us today and the staff that have come and gone on to great things. I think our openness, our willingness to collaborate has been, I don't think we've had a sense when we've turned down any other organization or tried to run roughshod. So we have tried as much as we could as the new kid on the block to be a collaborative player and model the behavior inside the same as we wanted outside. Sorry, last question? Oh, so I get to choose. Okay, I'll do both really quickly. Really quickly. First time GA4GH, don't be shy. Find a friend, find 2 friends, talk to somebody. Whatever you do, not picking on you guys standing at the back, but don't stand against the wall and watch the room. Get involved. Find somebody you recognize, find a common project, go up and talk to the speakers. They're all approachable. No, more questions keep coming. All right, we'll have to answer them separately. Definitely a huge part of our next phase is more global inclusion, including Africa. We've been fortunate in the continent of Africa. We've had H3 Africa and some great leadership in that. So we've been able to leverage that investment, not as easily in Asia or as in Latin America. So I think we've got work to do on all continents, particularly in the South. And I'll do just the one thing that was in the white paper that didn't work out. It envisioned a network of, let's say, 12 institutes who would operationalize the standards of the GA4GH in a few centers of excellence. And the world would send their genomes to a few centers, operating entities, we call them. That's not what happened. Every time we talked to another group, another funder, another organization, they said, no, the whole point about genomes being more cost effective is we can do them locally. We want to learn. We want to be able to do the work ourselves. So don't tell us, send our genomes somewhere else. Tell us what we can do to do it. But since we're all going to be doing it, find ways that we can share and interoperate and standardize. So increasingly we shifted to APIs, to federation, and truly to interoperable standards. That was the big difference. Okay, I'm going to stop at that point now. It's been a great pleasure to be here. And once again, thank you, Ewan, and really looking forward to working with Heidi. I think I chair the next session, which is implementing GA4GH in real world, and I'm waiting for the bios to arrive. And I'm going to have to wait for my glasses to arrive. Are they? Oh no, it's all right. They're in my pocket. So we're going to focus on real-world examples of GA4GH in use. It's a great pleasure to introduce a tag team. Are you coming up together, or are you coming up one after the other? But the data infrastructure, which is the realization of the Beyond 1 Million Genomes initiative, is probably going to be the largest implementation of GA4GH standards that we've seen to date and that we can envision. And so in bringing up, we're going to hear from Dylan Spalding. He's a senior coordinator for Elixir Finland at CSC. He's co-lead of Pillar 2 in the Digital European Genomics Data Infrastructure Project, and he's worked on other H2020 projects such as Sinica and Beyond 1 Million Genomes. And prior to joining CSC, he worked at AnVIL EBI, where he's responsible for EGA services in that organization. We're also going to welcome one of those people at the bottom, the grayed out people from below the line, who didn't go very far. Melissa Konopko is a scientific product manager at Elixir Europe, working with the Human Genomics and Translational Data team. Her primary focus involves creating harmonizing tools that guide countries along international interoperable pathways to advance their genomic and related data infrastructures. She led the development of the Million Genomes Framework, the Elixir Human Genome Data Maturation Model, and she was also a key member of the GA4GH staff as a workstream manager, and went on then to lead our initiatives in things like EDI. So it's a great pleasure to welcome both Dylan and Melissa to the stage.
The green button. Thank you. All right, I guess I get to. All right, so I'm going to introduce the European Genomic Data Infrastructure Project, and then I'm going to pass it over to Dylan, who's going to give you the real information. I'm just going to give you a little bit of context and background so you understand all of the technical bits. But he's going to talk about the framework that we have created and implemented a full suite of GA4GH standards and the plans that we have going forward into the future in order to help advance them as well as our infrastructure. So it all began with the 1+1,000,000 genomes declaration, and that was 25 European countries have agreed to cross-border access to genomic data. And the Beyond 1 Million Genomes project began after that in order to start to really design the infrastructure and to create a lot of these standards, or a lot of the software and tools that were required in order to support this infrastructure. After this point, the European Genomic Data Infrastructure Project began just in 2023 in order to implement the entire infrastructure that has been designed, and we are continuing to do development as the countries start to work on it. So the GDI project is to establish a federated, sustainable, and secure infrastructure based on community standards via the 1+1,000,000 Genomes Initiative. So the goals for that is to enhance research and to enhance personalized healthcare and for health policy making. It's an enormous project. It is 40 million euros. It's for over 4 years, and it has currently 20 countries, and there are actually more signing on right now. The project is structured under 3 pillars. There is the pillar 1, which is the sustainability pillar. It is focused on the governance model as well as the business model. There is pillar 2, which is the main technical pillar, and that is one of the ones that Dylan helps to run. They are developing the GDI starter kit, which is different from the GA4GH starter kit, and he will be talking more about that in detail later. We're also working on the data management plan in that pillar. Pillar 3 is the use case pillar, focusing on making sure that the infrastructure that we're creating is useful. So it is looking at various use cases, including the Genome of Europe project, which is upcoming, as well as federated learning, and it is all coordinated by the Elixir Hub where I work. So I mentioned before, B1MG, the infrastructure proof of concept was developed, and it is now moving into GDI, which is focusing on delivery and deployment. And all of the countries that have signed on to this have agreed to reach one of 3 levels. Either they are going to be at the onboarding level, which is more of the design and testing phase, the deployment level, which means they're going to be operational within their own country, or at the operational level, which means that they are going to be fully connected to the rest of the network. And the countries are going to choose this level based on the abilities that they have technically and with the kind of staffing and funding that they have in order to reach that within the time frame. As we start to implement the infrastructure that has been developed, we are going to be working with the countries who are doing this, and they're going to be giving us feedback and telling us what kinds of issues they're coming up with in terms of national policy, as well as technical issues, and that's going to be fed back into the infrastructure, as well as back to GA4GH in terms of standards development. We'll also be looking at new emerging technologies, and the use cases are going to be feeding back into this so we can make sure that the infrastructure that ultimately gets implemented is as useful as possible. So as mentioned before, it is based on 20 countries, and each of these countries have agreed to provide a data hub. They'll be managing their own data. And the data hubs are going to be providing the cross-border analysis and common framework based on a lot of standards and APIs. And this is mainly GA4GH, but there's also ones that are ISO and some that are European Commission-based standards. And that's also going to be something we want to feed back to the GA4GH community, because if GA4GH standards want to be used throughout Europe, a lot of these standards like EID, and EU Wallet, and DCAT are going to be important to connect with going forward. The entire infrastructure is based on the 1+1,000,000 Genomes data infrastructure project. So it's these 5 main functionalities. And you'll see a lot of similarities to some of the GA4GH work streams, but they don't align perfectly. But the entire infrastructure that is being designed fits within these categories here of data discovery, access management tools, data processing, data reception, and storage and interfaces. And from here, I will pass on to Dylan very shortly to talk about the starter kit. As I mentioned, a little bit different from the GA4GH starter kit. So what this is a set of software that is layered over the standards that we've chosen to ensure interoperability. And these pieces are being given to the countries to implement, and they can choose whether they want to use that exact piece or if they want to choose a different piece of software, but still making sure that it's layered over the standard. It was created just this year by people from a host of 18 countries, and Dylan did an amazing end-to-end demonstration at the Elixir All Hands. I'm seeing Angela shaking her head. Both her and I had like tears in our eyes, not even joking. It was exciting. Anyway, so I'll pass it over to Dylan to talk about that demo.
Okay, thanks. So Melissa mentioned the 5 functionalities. So we had to try and implement these 5 functionalities into this starter kit. And one of the things we needed to do was allow data discovery, which is the first functionality. So this means you have to have some level of public visibility to search for the genomic data. Now this will be aggregate or metadata that's non-sensitive. And then you can do that query from a user portal or data catalog. Then you want to go deeper into that, so you use then technologies such as Beacon and linking a beacon to a network of beacons across all these 20 countries. And then this allows a registered user using something like the Life Science AI to do a beacon query which will link genomic, phenotypic, and possibly clinical data in your query. And so some of the elements of we've got also then is Duo, which is data use ontology. That helps you find the data that is relevant for your research question. So once you found the data, then you need to try and gain access to it. And so this is functionality, the data access management. And so we had some of the GA4GH standards we used for this are the passports and the AAI. And we used a tool called Resource Entitlement Management System, or REMS, which can issue these passports via the Life Science AI and allows you to apply it for access to data, but also allows the Data Access Committee or Data Controller to log in and grant or deny access to that data once you've requested access. And it can also track the whole process, the ethics approval, anything that you need to do to allow that to come on. This would actually link in to a centralized user portal, which is where you've done your discovery query and now you're applying for the access. Perhaps, obviously, you need somewhere to store the data, and so we have the storage and interfaces. Now, this is how you store the data, and this is also the set of APIs that allow you to access the data from that storage. And this needs to be standard-based, so it's interoperable. And with all these things, we're trying to leverage existing open source implementations that already exist. So for example, with the storage and interfaces, within the starter kit, we used an implementation of a federated EGA node to provide the storage interface functionality. Some of the GA4GH standards, again, utilized here would be Crypt4GH for the encryption, and we'd also be looking at DRS and, again, passports for the authentication and authorization. Another functionality is the data reception. So this is how you get the data in and also out of the infrastructure. But it also defines how you represent the data you're bringing in and the kind of quality control mechanisms you apply for the data when you bring it into the infrastructure. So this helps harmonize the data across all the countries and make sure it's interoperable and the analyses you do are comparable across all the different countries. And some examples within Starter Kit that apply for this functionality would be the synthetic data. So we use synthetic data initially, so there's no risk of leaking data about participants or anything. And so we would use things like phenopackets, VCF files, Babb and CRAN would all be part of this, representing the data that comes into the infrastructure. And when it comes out of the infrastructure, should it come out of the infrastructure? And XGS-GET, for example, also is a transfer protocol which would allow data out should it come out of the infrastructure. And then there's what we call processing. This is kind of data analysis or compute. And so this is where you perform the analyses on the data that you've got access to. Within the starter kit, we had two types of ways of doing this. There was what we call containerized computation. So these would be containers that you use to run a pre-built container, Docker or something, which would run an analysis on the data. But also we use the GA4GH standards with TES, WES, and TRS to allow you to define workflows and federate these across the whole infrastructure. So the idea would be that you would have these secure processing environments, perhaps one or even more in each different country. And so your analysis could go across there, or you could just distribute these containers, depending on your particular use case. So within the starter kit, we wanted to demonstrate a real kind of user story. So within the 1+1,000,000 genomes declaration, there are use cases, and we had rare disease and cancer use cases, and we aggregated their kind of user story into a generalized one that's on the screen. So here the user would discover a phenotype of interest with aggregate data, for example, by the user portal. Then the user would log in via Life Science AI at registered level and would discover a genomic variant and treatment regime and or phenotype of interest. Then they'd apply for access, the Data Access Committee would grant access to a virtual cohort, and the user would execute an analysis as a controlled access user on this virtual cohort across these federated locations. One of the things with the virtual cohort is to conform with data minimization principle within GDPR. The data the user would have access to would be based strictly on the research question they want, so they'd only get data relevant for that research question, and they wouldn't necessarily know the location of the data across the whole of the GDI. So here we can see at the bottom how the GA4GH standards support the functionalities right at the top, and then this how the starter kit allows this user story to go along. So from the user portal to the access, to the using beacon, to Life Science AI and passports and REMS, then the sensitive data, and then the synthetic data and data reception and HGS get, to finally the containerized computation and the federated compute at the end. So the actual starter kit itself is deployed at each different node, and this is at the bottom level here, this national part. So the nodes would deploy a different starter kit, and we tried to demonstrate that in June, where we demonstrated deploying a starter kit. It took about 15 minutes. You then link that and register that to a beacon network and onto the Life Science AI, which uses passports, and this provides European connectivity. So then we demonstrated queries across 5 different nodes at the time. There are 6 now, all of which have deployed a starter kit. And then in future, and it's being developed, is this user portal, which will sit over the whole top of the thing and then allow that single point of query and data access. These are, I mentioned, we want to use open source products where possible. So here's a list of some of the things that we were using. Some of them are already in production. Some of them still need work to bring up to production level. And we also used different countries to drive the development of these, and these were called Vanguard nodes, and each one had a product owner who was assigned the task to ensure that that particular product supported the GDI requirements. And so this helps onboard different countries, improves collaboration and so on.
Sure. Okay, just to wrap things up really quickly, you can see that we've got a lot of plans going forward. One of the big ones that we really need to make sure we're aligning with is the data protection by design and default principles. And the Genome of Europe project is going to be underneath this. It's going to be it's going to be 500,000 genomes that are going to be put into the infrastructure. And so as we engage with GA4GH, we're also going to be trying to reflect the needs of the Genome of Europe. And I hope that as you're all listening to this, you're like, wow, this is a really big deal. How do I connect up with it? And there is a website that is available that it has all of the lists of resources and recommendations and tools that is so easy to find and use. And we have the link to that available, and I'm sure we can work with GA4GH to send that out, because we list loads and loads of GA4GH standards and link out to you guys there as well. So that is us. Do we stay here?
We stay here or go back and come here.
I can chill here.
Well, we will need one more chair. So thank you both. You can see why Andrew and I were so excited when we saw this at scale back at the Elixir All Hands meeting. It's a great pleasure to introduce our next speaker. Again, if I get my glasses on so I can read. It's Professor Soichi Ogishima, who has been a long-time contributor, supporter of GA4GH, has carried our flag very high in Japan which is not always the easiest country to generate genomic data sharing, but Soichi's been a constant voice from his capacity both at the Tohoku Megabank, university, and through the Japanese Biobank, and a great technical contributor, including in Sendai with workshops and hackathons and really bringing it to life in Japan. The scale of which they're operating is significant, and it's across many aspects of work in Japan. Soichi, it's a great pleasure to welcome you to the stage.
Thank you very much. So, hello. So thank you very much for your very kind introduction. So I'm very happy to be here. So I'd like to talk about the development of the biobank network in Japan as a trusted research infrastructure for precision medicine. Next slide, please. So the biobank, as you know, the biobank is a trusted research infrastructure that collects the biospecimen data from donors and makes them available to the researchers. In order to establish a trusted research infrastructure, various technical standards are needed, and the GA4GH technical standards are very important. Next slide, please. I participated in the Tohoku Medical Megabank project, and I have been involved in the development of the infrastructure for the population biobank. So the Tohoku Medical Megabank project aims to elucidate the interplay between the genetic and the environmental factors that cause common diseases, and to develop the personalized health care through the risk prediction. To clarify interplay between the genetic and environmental factors causing common diseases, we conducted prospective genomic cohort studies to collect blood samples and exposures and have digitized the DNA to genomic data as genetic factors. And as a molecular phenotypes, so we digitized plasma to metabolome protein data. And we have collected the clinical data through hospital information system as a more clinical phenotype. Next slide, please. So in the Tohoku Medical Megabank project has collected the exposome and clinical data, and now we have conducted 100,000 whole genome sequencing. So we collected 100,000 of the extensive phenotypic genotypic data and biospecimen from Japanese population, and integrate all the data into one database, which we call DBTMM. The DBTMM integrates all the collected data. Next slide, please. Thank you. So for data discovery in pre-research phase, so researchers from academia and industry can preview the individual data on the DBTMM before the approval of IRB. And the next slide, please. Yes, researchers can access and search the Japanese population and browse the individual data of the stratified population in the data table and visualize the statistics in the graph. And researchers can also explore the statistical characteristics of the stratified population compared to the mass population as the feature extraction. Next slide, please. After approval of the data access committee, researchers build cohort and use the data retrieved from the DBTMM in research phase. Next slide, please. So I presented the biobank of the population cohort of the Tohoku Medical Megabank project. Next slide, please. In Japan, there exists over 50 biobanks. So Japanese biobanks stores extensive, previous slide, please. Okay, thank you. And the Japanese biobanks, so we have over 1 million biospecimen provided by over 700,000 donors are available. As East Asian biobanks, it is very important that the Japanese biobanks promote the use of a very large number of the Japanese population's extensive phenotypic and genotypic data and biospecimen for the precision medicine research. Next slide, please. So for promotion of the use of the extensive data and high-quality biospecimen in our biobank network, in biobanks in Japan, we started an aimed project establishing a biobank network in Japan and developing a trusted research infrastructure. So based on the DBTM technology established in the Tohoku Medical Megabank project, we have developed a biobank cross-search system for biospecimen and data across biobanks and have built a one-stop service to provide access to biospecimen data stored in our biobank network. Our biobank network has grown up to the over 500,000 donors and 1 million biospecimen and 300,000 genomic omics data. Next slide, please. So for academic and industry users, our biobank network provides biobank cross-search system. So to find to search the biospecimen data with the condition of the positive transgender, disease history, biospecimen type, disease name, and so on. And of course, the user can search the data, genomic and omics data in our system. And if the user find a suitable biospecimen and data in our biobank network, so they can inquiry to each biobank and can apply to use the biospecimen data in biobank network. So to provide a biobank cross-search service for biospecimen data, we standardized the metadata of biospecimen data, and the metadata was standardized by the minimum information about biobank data sharing, MIABIS, in accordance with the biobank data model of the European Biobank Network, BBM-ERIC. The next slide, please. Thank you. So the biobank cross-search system is a web application and can be used after the user authentication. So user can view detailed individual data and must agree to terms of use as a registered access. Next slide, please. Thank you. So the user can search by disease name, by genomic omics data type, and by specimen type, and dual code. So the users can search by selecting ICD-10 and codes hierarchically, and more than 8,000 diseases are covered. So, and the user can also search for biobank specimens that have undergone the genome analysis. Next slide, please. So the user can browse a list of biospecimen and data that match their search criteria and list the sample of data of their interest. And the user can explore the donor individual data in detail for the data discovery prior to the application to the research use. So user can draft up a research plan. Next slide, please. Yes, and once a research plan is drafted, the user can inquire with the biobank about the use of the biological samples and data, and obtain after the approval of the IRB, so apply to the biobank network for use of the specimen in research, so in a one-stop application process. Next slide, please. So our biobank cross-search system is federated search system, which consists of the central cross-search system and the biobank node databases. And each biobank has each biobank node, and the central cross-search system accepts a search request to the biobank nodes and returns the search result from the biobank nodes. And central cross-search system receive a HTTP search request from users, and the central cross-search system node makes a query for each biobank node database by using API. So this API is now being standardized internationally in ISO community, but at the same time, I think I would like to harmonize it with the GA4GH Beacon standard. Next slide, please. So biobank network is a global trend. So we have ISBA, it's an international society for biobank, and the BBM-ERIC also work on the biobank networking. Next slide, please. And the German Biobank Alliance at BBM-ERIC DE has made a sample locator publicly available, and allowing searches across German biobanks of the 500 samples from 100 donors. So we launched this service in October 2019, the same month we did. So we recently visited BBM-ERIC in Graz and confirmed that we will collaborate with the BBM-ERIC Biobank Network. And it is very important that the EU and the Japanese biobank networks collaborate on a common standard so that biospecimen and data can be discovered and applied for use. Next slide, please. Thank you. So various technical standards required to build a trusted research infrastructure for biobanks, and the GA4GH technical standards are very important. And in our biobank network, we have implemented data use ontology and pinned packets technical standards. Next slide, please. Thank you. So user can search for data held by major Japanese biobanks with standardized terms of use through the data use ontology, and download the standardized clinical phenotype information through the pinned packets. Next slide, please. And the researchers benefit from the GA4GH data use ontology and pinned packets technical standards. So donors benefit as well as the researcher. Don't you think so? So in the trusted researcher infrastructure of biobanks, it is important to obtain appropriate informed consent from the donors. It is important to make the content of the informed consent easy to understand for participants, for patients and citizens. Next slide, please. So data use ontology standardize the data use condition. Dual codes can be used to code the data use condition based on the consent forms. And dual first codes whether the data may be used for research on disease-specific medical research or research in general. And then clarify this with a modifier. Next slide, please. Yeah, and the essential point in the term of the data use in for what and by whom it may be used. So we recognize the dual codes from the permission and we reorganize the dual codes from the permission and modifier to for what purposes, by whom, and modifier. Next slide, please. Next slide, please. Thank you. In order to make the content of the informed consent easier to understand for patients, we have studied the implementation of the e-consent using the dual code. So patients first decided for what purposes it may be used, whether the patient wants the data to be used for the research on the same disease, for medical research, or for research in general. And patients then decided who may use the data, whether it were to your doctor, or to your doctor's collaborators, or domestic researchers, or the foreign researchers. So this e-consent allows the patient to determine the purpose and the scope of data use in an easy to understand manner. So we believe it is very important, this common e-consent form, to be used in every study. So we believe that this will make it easier for the patient to consent to the precision medicine research. So you can see a pictogram of the dual code. So next slide, please. The Japanese dual group has developed a pictogram to make dual code easier to understand. Next slide, please. Yeah. So now we have built the trust research infrastructure for biobank. So we have established an infrastructure of data and participation. So next slide, please. So one more thing, so DDBJ has implemented the GA4GH WS technical standards called Sapporo with controlled access, and the DBJ has started operating the workflow already. So it is important to build a secure research environment that complies with GA4GH technical standards. Next slide, please. This is the last slide. So as I mentioned, we have worked on the build up the trusted research infrastructures. So by using the GA4GH technologies, so the realization of genomic medicine requires the precise identification of the genetic determinants of disease leveraged by the population-specific genetic backgrounds and phenotypes. So as East Asian biobanks, our biobank network in Japan is responsible for providing the extensive phenotypic genotypic data and biospecimen from a very large number of Japanese population. Next slide, please. So thank you so much for your attention.
Oh, there she is. So I knew exactly where our next speaker was sitting before. Then she moved, and I spent the last 3 minutes trying to find her in the audience. So another great example of GA4GH former staff staying close, staying connected, and then coming back to work with us. So it's a great pleasure for me, personally, to invite Dr. Rachel Liao to the stage. She's head of scientific strategy at the Broad. She works in the data sciences platform where she leads strategic partnerships with academic and industrial collaborators to enable research into genetics and genomics at scale, leveraging cloud products developed by DSP, the data science platform. She works with the Bro's Chief Data Officer to lead NHGRI's analysis, visualization, and informatics, better known as AnVIL, lab space, a data program currently storing and managing more than 10 petabytes of data. Rachel, welcome to the stage.
Thanks, Peter, and thanks to the organizers of the meeting for inviting me to speak today. I am delighted to be here. As Peter said, I have a long history with GA4GH. I joined as staff in March of 2015, so not right at the beginning, but very early on, and have been just thrilled to be a part of this community. I am also thrilled to be presenting to you today on the Analysis, Visualization, and Informatics Lab Space, the AnVIL, funded by the National Human Genome Research Institute at the NIH here in the US. I'm PI on that award at the Broad Institute, and I am really excited to talk with you today about how we are leveraging GA4GH standards to make more than 5 petabytes of released data and over 5 petabytes of pre-release data secure and, when appropriate, accessible and usable using standards developed by this community. Here we go. So let's get started. So first I want to just draw your attention to the level above the AnVIL in terms of organization. AnVIL is part of a network of interoperable data repositories called the NIH Cloud Platform Interoperability Effort, the NCPI. Peter actually referenced this in the previous session. This is a new driver project of the GA4GH. So we're really excited for the AnVIL and for that effort to be also more engaged with the GA4GH community. NCPI has recently funded several interoperability projects for the first time, including projects that include the AnVIL to increase data sharing and joint analysis among all of these repositories. Just very excited for a little bit deeper dive on the AnVIL, but all of these are our partners as we think about data sharing and access. Let me talk a little bit about the AnVIL. As you can see here, the AnVIL is comprised of 3 pillars of work to support researchers. I won't go into great detail here, but very briefly, the AnVIL brings together first large and diverse data sets for cloud storage and access alongside of other data sets stored and accessible in the Terra platform. AnVIL leverages elastic and scalable compute environments in the cloud in order to support bioinformatics tools, allows users to build, share, and deploy pipelines of their choosing. And AnVIL brings together a diverse community of researchers to collaborate, share, and learn and drive forward scientific discovery. AnVIL also is maintained in an environment that is fully FedRAMP authorized and compliant, which is a high security standard here in the US maintained by the federal government to ensure the security of all data stored in the platform, which is of course incredibly important to us as we are custodians of these federal data sets that have been funded by the taxpayers and are important for the scientific impact for the country and the world. So let's talk a little bit about the AnVIL system. AnVIL, as we said, is a cloud-native platform with a goal to support diverse users for cost-efficient data storage and analysis. AnVIL enables users to do that by accessing data from multiple sources. As I said, linked NCPI program data, other cloud data repositories, as well as upload from users or from the on-prem data centers where users operate. In the future, we hope to support data submission from other tools such as REDCap that would allow us to collect even more diverse modalities of data, such as clinical data. And AnVIL is also in the process of taking advantage of the Terra platform's expansion into the Azure cloud, and will soon provide support for users to access AnVIL data tools and resources in both the Google Cloud and the Azure cloud. The initial AnVIL was launched in the Google Cloud only. And we're really excited for this, especially as the AnVIL expands its footprint to include more clinical data sets and to be in more clinical spaces in the coming years. And I'll talk a little bit more about that in a couple slides. Within the AnVIL environment on both clouds, of course, researchers will be able to access workspace data storage, workflow support, interactive analysis environments to support the variety of analyses that our researchers perform. Here, just a little bit on the basics of the data that we store in the AnVIL. There are many large and diverse data sets that have been submitted from consortia who have worked with us to structure their data in a way that will be most usable for their research communities. This data set, the AnVIL's data set is currently more than 5 petabytes, as I said, of release data, a little bit more than 5 petabytes of pre-release data. Those are data sets that are in the submission process. And the AnVIL was launched in 2018. So really, in the past 5 years, we have grown from no data sets in the AnVIL to more than 10 petabytes of data, which is really has been quite an accomplishment. Additionally, we are able to moderate data access in a flexible way to meet the needs of our researchers. So as you can see here, we have a data catalog that allows researchers to discover data without requiring them to have access to data sets, where they can then request access to data sets of interest through either dbGaP or through the Duos product, which I'll talk about a little bit later, for specific data access requests at the cohort level. And I'm very excited to talk a little bit now about the object-level data browsing that we're going to be enabling for our users through a newly released Data Explorer. You can see just a brief visual of the Data Explorer right here. This is a Data Explorer that's going to enable data discovery not at the cohort level, but at the sample level. So we'll actually be able to index across AnVIL data sets for a subset of consistent metadata fields. We've called this the findability subset, and that'll allow for cross-data set search and discovery. So not just within a specific data set or cohort, but across the various cohorts stored in the AnVIL, where researchers will be able to discover at the sample level any data set which they have access to. This will allow the creation of custom and cross-data set cohorts, which will then be able to be exported into a user's workspace environment for further analysis. And this is not released quite yet. This is in alpha release, so our internal community is currently giving feedback on this product, but we anticipate release to beta for the broader community in a matter of weeks. And I want to just point out quickly, this has been a close collaborative effort to work on this and release this Explorer with Benedict Payton and his group, and he's here today, so I want to thank Benedict for his partnership on this. Okay, so quickly, I want to step back for just a minute and speak about mention how what I've mostly just described is work that took place in the past 5 years. So that was actually during AnVIL's first phase. We were funded for 5 years, from mid-2018 to mid-2023. As a program established by the NHGRI to empower researchers by bringing together data tools and community support to do groundbreaking research. And this initiative was largely genomics oriented. That was the sort of data that was being generated by researchers funded by the NHGRI. Largely at the time, we prioritized data sets, tools, and applications well known to the genomics community. There was some specialized support for clinical data sets and other modalities, but largely, the AnVIL was led by 2 genomics organizations with strong track records, Johns Hopkins University and at the Broad, and we were able to integrate data sets and tools and analysis environments that you can see here that have been very supportive of our researchers over the past 5 years. In the next 5 years, I'm delighted to share that AnVIL has been funded for another phase of successful science, and in addition to continuing the work that we've been doing in the genomics community, we will also be expanding our team to include our amazing colleagues at Vanderbilt University Medical Center, led by Robert Carroll, who I know is very well known to this community, to expand AnVIL's focus into clinical data and research. And so we're really excited by the ways that this is going to expand the scientific impact, both of the genomics data that the AnVIL currently stores, as well as the data that are going to be stored in the future and the research that we'll be able to do. Okay, so now I'm going to move on to the part that I know you've all been waiting for, which is how AnVIL leverages the GA4GH standards that are developed by this community. And this section has been pulled together with support from many colleagues near and far. So I'm really representing the work and the efforts of many dozens of folks who have been involved in this work, both here in the GA4GH and within the AnVIL community. Okay, so I'm going to start with DIRS. GA4GH's DIRS spec has been implemented to support AnVIL data access. Released AnVIL data sets are stored in what we call the Teradata repository. This is a secure repository that adheres to the FAIR data principles that we know and love in this community. And we enabled data access from this Teradata repository using the DERS standard. To meet the specific needs of the AnVIL community, our teams have implemented some extensions that have been customized to really leverage the DERS spec effectively for the needs of AnVIL researchers, including some that you see listed here. So for instance, in the Teradata repository, we support multi-cloud DERS URIs. So we're able to use DERS URIs to, in a single deterministic way to enable access to data in whichever cloud the data will be currently located in. That's important as the AnVIL expands to the Azure cloud alongside of the GCP cloud. We've enabled aliasing of DERS URIs in TDR to enable AnVIL minted DERS URIs from other systems, for instance, the Gen 3 system, to remain accessible to our researchers even when the data are now hosted in TDR with a new DERS URI that's minted by TDR. As you can see here, this is done in TDR and in DERS Hub, the client that resolves DERS IDs within TDR, and production rollout is in progress. And TDR also leverages DERS in the context of data access payment options for the AnVIL. This is specific to the GCP cloud. Users are able to essentially either request that the user pays for any access charges or that the data storage, the host of the data storage pays for those costs in the GCP cloud. This is done and in production use and is a way in which I think we make the AnVIL data more flexible in terms of access for members of our community. There's also a back end to the AnVIL. AnVIL is powered by the Terra platform. It's an important program that's a driver project for implementing a lot of GA4GH standards in Terra for tasks, tools, and workflows that benefit not only the AnVIL, but all users of Terra. So as you can see here, Terra leverages TERS as a mechanism to get workflows from DocStore into our workflow engine Cromwell. We leverage WES, which is implemented in Terra to execute workflows in Cromwell. And TESS is now the backend for Cromwell workflows specifically in Azure, as you can see here. So these are, again, not specific to the AnVIL, but where the AnVIL has really been a driving project for implementation of these standards. And in the future, we see other workflow engines being powered by TESS. We see other workflow languages and services to execute workflows through WES. We see other ways that these standards could be leveraged in the future to really expand the opportunities, the options that are available to researchers in the Terra platform overall. This is a lot of technical detail, and I do want to just call out that my colleague Kyle Vernest is also here in person, and he can speak to a lot of these architectural details in with a lot more context than I can. So I recommend reaching out to him if you want to talk more. OK, so then the final product that I'm going to talk to you all about today in the AnVIL is Duos, the Data Use Oversight System. This is an important part of the AnVIL that has used GA4GH standards, has been a part of the GA4GH community and discussion, both in policy as well as in technical specifications to develop expedited data sharing and access processes in some of the ways that you can see listed here. There's a library card agreement in Duos that allows signing officials to pre-authorize users once, just making that process more streamlined. It allows for expedited workflows for data access committees, including batch voting, optional data access request automation, and then, of course, linking with the Teradata repository for automated user approval or even removal as updates are made to data resources. So ways that Duos is standardizing of what has, up till now, in a lot of contexts, been a very manual and time-consuming, laborious data access process. I'll speak just a little bit more detail about how Duos uses the GA4GH standards. For example, Duos represents user profiles that are aligned with GA4GH passport visa types. You can see them listed here in multiple different ways, straight from the Cell Genomics paper into Duos's profile. Duos also has the ability to help users draft consent form language based on Duo terms, so the terms that have been defined by this community that can then be represented in a consent form This is an early feature that has been really informed by the machine-readable consent guidance that's recently been an output of the GA4GH Ethical Provenance Working Group that was initiated over the past year. We see this as a really productive collaboration with GA4GH to standardize draft and consent form language. Duos overall was developed with the help of GA4GH's Data Access Committee review standards, principles, as well as guidance from the NIH data access committees, especially at the NHGRI. In the past several years, several pilots have been run to test its ability to really automate data access requests in real-life situations with real-life data access requests. And these pilots have been so successful that we're really excited to announce that NHGRI is now using Duos in production for data access requests. So the NHGRI has made the decision to use Duos for real data access requests for AnVIL data. This is a real shift in the way that data access requests are made for federal data in the US. And we're really excited that this is now actually online for only one data set, our most requested data set, which is GTEx. But even in a matter of months, we see this expanding to many, many more data sets, as you can see here. And we're really just thrilled with what this means for AnVIL grantees, for data, for folks who are going to be requesting data from the AnVIL in the future, and especially excited about how GA4GH standards have really facilitated the clearer and faster data access request reviews that are really making this possible. So really quickly, some of the next steps that we're following from that. Jonathan Lawson and colleagues who have been driving forward the work that has been done on Duos for the past many years in Terra have shown that this is not just going to support data access requests in AnVIL, but has the potential to manage access requests for 93% of NIH data sets today that are registered in dbGaP. That is to say that 93% of NIH data sets can be mapped to Duo codes for straightforward management using the Duos system. And so we see that as a real opportunity for the way that Duos could be expanded to other NIH data repositories in the future. And this is timely because this aligns very nicely with the additional expectation for data sharing that was recently released by the NIH called the new Data Management and Sharing Policy. This requires researchers who are funded after January 25th, 2023 to submit a formal data management and sharing plan outlining how their scientific data will be managed and shared and requiring deposit to an approved repository. Because of AnVIL's commitment to standardizing secure data storage and access and analysis, and in large part due to what I see as the incredible and supportive community of GA4GH over the course of many years, as well as the vision that our funders at the NHGRI have had for this repository, AnVIL is really well positioned to drive even more impactful data sharing and analysis because of this policy, as a result of this policy, being really a really well-positioned data storage solution for researchers across the NIH. So with that, I will thank you and thank everyone who has been involved in the AnVIL program, especially our funders, many of whom are here today in person, and of course, again, to the organizers for this opportunity. Thank you.
As you can tell, both from the agenda and from the format, we're going to take questions afterwards. So if you've got really great questions, I think we'll be using Slido for it. So think if you want to target it to one of the speakers, please do. If you want to make it more of a general comment, let us know in Slido how you'd like me to direct that. So the last speaker of this session of GA4GH in the real world, it's another great pleasure for me personally to introduce Marc Fiume. Marc is the CEO of DNA Stack, a longtime contributor of GA4GH. He's the former lead of the GA4GH Beacon project and co-chair of the Discovery Workstream. The driver project champion for Autism Sharing Initiative. He and his team have several national and international data sharing platforms, including Beacon Network, Viral AI, Neuroscience AI, which we'll hear about more today. And just as I pointed out that Melissa and Rachel used to be part of our team that stayed close to us, went to somewhere else, Marc is doing his very best to keep former GA4GH employees close to us and continuing to work on the development of GA4GH standards just from the other side of the street. Thank you, Marc.
Thanks, Peter. I keep telling you, you should take that as a compliment.
That's right.
It's a great privilege for me to be here to celebrate 10 years of impact of the GA4GH and want to congratulate my colleagues on the tremendous progress you've made in driving forward on implementation. So today I'll be telling you more about some exciting progress we've been making with the Autism Sharing Initiative in creating a global federated network for autism and neuroscience. So today we'll share 4 points here. We have made progress towards building a global federated GA4GH compliant network of really high-value data sets in autism. We're working hard to expand our work in autism across other areas of neuroscience. We'll share exciting news that happened just this morning where we launched a new software platform that's accelerating our ability to support GA4GH adoption. And lastly, to talk about new progress we've been made to validate the ability to run GA4GH compliant federated learning. So autism is characterized as a spectrum of differences in social skills, repetitive behaviors, speech, and nonverbal communication. 1 in 36 children in the US are diagnosed. And because it is a spectrum, it is incredibly diverse. Therefore, we need lots and lots of data. The figure on the right shows our ability to power new discoveries as a function of the sample size, and that's measured in thousands. And the conclusion that we draw from this is that we need to work together. So we founded the Autism Sharing Initiative on the premise that by connecting the world's autism data, genomics and otherwise, we can help scientists get to that inflection point in discoveries much sooner. So we're so excited to have partnered with 3 organizations who shared in that vision. It was a wonderful national and international collaboration with 11 public and private sector partners to execute on a roadmap that took 18 months to deliver a platform that we call Neuroscience AI. So Neuroscience AI is a global GA4GH compliant federated network for high-value data sets in autism. And at its launch, we had contributions from really great partners like University of British Columbia, Sick Kids, Autism Speaks, Holland Bloor View, Aims to Trials, Sidra Medicine, and great collaborators at Roche. So if you go to neuroscience.ai today, you'll see this interface. And while it looks and feels like one database, it is truly a federated repository where each of the data sets you see represented as a card has been contributed by a different data steward and is physically and administratively controlled by their respective data stewards. So in much the same way that Beacon unifies the experience of searching across a network of beacons, Neuroscience AI attempts to create a unified interface and experience for searching across a global network of autism data. So you might be wondering, why did we call this Neuroscience AI and not Autism AI? And that's because autism is more than its core symptoms. Every person with autism is truly unique and may be affected by a number of different co-occurring conditions. For example, 50% of people with autism have ADHD. 30% of people with autism have epilepsy. And while autism and aging with autism is relatively understudied, there's increasing evidence to suggest that 1% of people with autism will develop Parkinson's over time. So autism is related to many other conditions like ADHD, anxiety, bipolar, depression, epilepsy, GI, schizophrenia, sleep. And all of these things impact quality of life and imply a shared biology. So our thesis now is that the best way for us to be able to understand autism is actually to study it in the context of related neurodevelopmental and neurodegenerative conditions. So if we want to build a global federated network of data in neuroscience, how can we make that scale? We're all here because standards are important, but they are also pretty hard. And if we're going to be successful in our mission, we need to make it much easier, faster, and less expensive to adopt GA4GH. So that's why we're incredibly excited to introduce Omics AI. Omics AI is a new platform we launched just this morning that provides the ability to have production-ready software for creating GA4GH compliant networks and analyze across them. And to mark the launch, we made this little video. It's not as well commented as Angela's, but here we go.
We're so excited to introduce Omics AI. Omics AI is a software suite made up of 3 revolutionary products: Publisher, Explorer, and Workbench. These products work together to empower scientists to derive insights from data wherever it lives. Publisher increases the impact of your data by making it possible for you to organize, govern access to, and connect it into global networks without giving up control. Explorer is a beautiful, customizable portal that makes it easy to find, access, search, and analyze data sets that have been connected through a federated network of publishers. Finally, Workbench helps you generate insights by making it possible to perform custom and best practices data analyses, including federated learning, without needing to move data outside of secure, trusted environments. We are big believers in open science. That's why, from how users log in to how data are represented and computed on, Omics AI has been engineered from the ground up to implement open standards by the Global Alliance for Genomics and Health. These standards ensure maximum interoperability and enable an open innovation ecosystem for our community to build yet unimagined extensions. Omics AI is a breakthrough in our ability to harness the collective power of the world's omics and health data and forge the future of collaborative research. We can't wait to see what you discover with it.
All right, so our team was really excited to push for the launch of Omics AI this morning. And it represents 10 years worth of course, standards development and implementation. What Omics AI really is a productization of collaborative work we've done together with the GA4GH, especially the Federated Analysis Systems Project, or FASP, where we showed how we can combine multiple GA4GH standards together to create production-ready systems. So the key benefits that we'd like to drive with Omics AI for our own team and our partners is to make it easier, faster, and less expensive to drive the adoption of GA4GH standards into the world. So Omics AI is helping us to expand the universe of GA4GH compliant in neuroscience and beyond. I want to talk about a couple examples of partnerships that we've made since launching neuroscience. So the first one is with a funding initiative called Aligning Science Across Parkinson's, or ASAP. They have the mission to accelerate the pace of discovery and inform a path to a cure for Parkinson's. And we're working together with our partners at Verily, Data Technica, and the implementation partner, which is the Michael J. Fox Foundation, to build a collaborative research network. A second example is with Target ALS. It's a medical research foundation committed to the search for effective treatments for ALS where everyone lives. And we're working again together with Verily to implement a data platform powered by GA4GH standards. Finally, the Canadian Platform for Genomics and Precision Health is a highly collaborative, federally funded effort to expand interprovincial, national, and international networks in neuroscience, oncology, infectious, and rare disease. So what next? We have this ability to build networks. Now we're exploring how we could apply latest technologies in federated learning to make discoveries across federated networks without moving data. And to execute on this hypothesis, we teamed up with a brilliant researcher. Her name is Dr. Azadeh Kushki at Holland Bloorview Hospital in Toronto, in collaboration with Integrate AI, to explore how we could use federated learning across GA4GH networks to answer one question. That question was, are demographics predictive of medication use in autism? So we wanted to run this experiment across 5 pediatric hospitals, each with its own privately controlled demographic and medication use data. What we did is we installed the publisher for each organization in order to standardize data across each of the sites, and we also installed a locally controlled workflow execution service. The next thing we did was we connected each one of those WESs to a workbench, which is our workflow execution delegation system, And Workbench has a unique ability to manage a workflow execution across multiple engines simultaneously. So we use Workbench to now send Wes a WDL and an untrained model to each one of those organizations, where the local Wes's computed to train models without moving data. At the end of that training exercise, the Wes's send locally trained models back to Workbench, which aggregated those models back into a single model itself. So we're really excited, not really for the scientific outcome of this project necessarily, but as a technical demonstration that it's possible to conduct privacy-preserving federated learning following GA4GH standards. In this example, we were able to successfully train a federated learning model that could predict medication use by diagnosis, where we found that there was 30% higher use of stimulants by people with ADHD compared to autism, and there were 10% higher use of antipsychotics by people from lower income families compared to higher income families. But now that we've validated the potential to do this kind of model, we have lots of enthusiasm for connecting more information across a larger number of collaborators. So this is a really exciting outcome for us, an opportunity for us to grow. So in summary, in the Autism Sharing Initiative, we've now built a global federated network in autism. We're expanding that network across multiple areas in neuroscience. We've launched Omics AI to accelerate the adoption of GA4GH standards and are working to prove the ability to perform GA4GH compliant federated learning. So with that, I would just like to, again, kind of reflect on 10 amazing years of collaboration with GA4GH, and thank you all. We would not have a way to pursue this mission without you.
So I think the comment across all the presenters is it works both ways. Without you implementing it, without you giving us the feedback, without you operationalizing it, we wouldn't have GA4GH. So it's not coming from GA4GH and being thrown over to you. It's this constant cycle of knowledge and learning. So I assume Slido is now going to pop up incredibly challenging and exciting questions for our speakers. First one, let's just take them in order. Melissa, can you see that?
Yeah, it's still Dylan.
Is there any way we can turn that around?
We've seen some gaps that we think exist. There are things like, for example, keys for encryption for GA4GH, for GH, distribution, how you distribute those with DRS. There are possibly things in terms of an individual's use of data. So, for example, an individual may have different roles or responsibilities depending on their identity at different institutions. They may be a doctor at one institution but a researcher at another institution. And so looking at the actual use of that user wants to make of the data when they're trying to access the data. So that's another thing. But this is all just starting to appear. We're starting to get this feedback now from the different users of the starter kit.
Okay, you were actually going to be up next, Dylan, with another question, but it got bumped in the upvoting process. So the next question is, we all talk about these data environments that we're building. Is there good information about the impact that these platforms and the standards that support them are having? How do we make sure that our efforts, where do they go? That our efforts are having impact so that we are not just paying lip service to each other. So rather than just saying we all built these great GA4GH things, what impact do you see them having today or in the immediate future, since we're in the real world? Who wants to go first? Nobody. We're going to have to pick on somebody. Mark, you go first.
Gosh, well, I think making data standardized and available is the first way to quantify impact. Of course, we want to get to the point where we are making discoveries, but I think making sure that the data are accessible and useful, and to do so in a way that's standardized such that people can really start at doing data science. Doing AI, about 80% of the work in doing artificial intelligence and machine learning is preparing the data to do so. So I think the major feedback that we're getting is that by virtue of the data being standardized across this network, that we can do science faster.
Okay. Rachel?
Yeah, I think the way that we measure impact is thinking about where we were 10 years ago in terms of the ability to share and access and jointly analyze data. I did a lot of my thesis research on, using the Cancer Genome Atlas data set funded by the National Cancer Institute in the US. And we used to send data on hard drives through the mail, and nobody else could access it besides whoever it was sent to. So I think that the fact that we can now leverage standards for sharing data across platforms, across countries and continents, really demonstrates that the impact of these systems has been significant for getting us from where we were to where we are today. That being said, of course, there is always more to be done, and so I think that's why we're still here. I'm sure that's what the next 10 years of GA4GH is intending to move forward as well.
So I think you're also speaking to it, whoever's asking and upvoting the question, it's also speaking to one of our perpetual challenges. We push the standards out, we find out about many of the implementations, but by all means not all of the implementations. And what we often don't find out is that next level. So when these standards were used at scale, when they were used in the real world, what scientific or medical breakthroughs actually took place that we can trace that provenance all the way back to a GA4GH standard. And it is a big global environment, and it's one of our biggest challenges is finding those real impact statements. So if anybody's got any ideas, we talk about DOIs and we talk about citations, but in our world, finding out that this standard implemented in this way created that outcome for an individual or a group of patients is very difficult to keep tracing all that way back. Marc, I'm going to stay with you. What role do families and individuals with autism play in your data sharing initiatives?
Yeah, this is a great question, something that we are highly conscious of and want to do more of. We have autistic representatives through, say, Aims to Trials or in our partnership with Autism Speaks that regularly engage with the autistic population just to empathize with how they view their position in biomedical research. One thing we've learned is that it needs to be much more of a two-way street than it has traditionally been. It is not just let me have your data so that I can analyze it. So you saw actually in our presentation the shift towards focusing on co-occurring conditions. Help me with my pain or my GI or my sleep. I'm not so concerned with the core symptoms of autism. Let's focus on the things that improve quality of life. So we're pretty actively involved with families and individuals to that effect. Yeah.
Okay. It is fun working Slido as things jump up and down and disappear completely. We have a new leader. As the numbers and there was one and I'll probably come back to finish with that at the end. There was one that's gone through there which said, what are the biggest hurdles in implementing standards? So if you can think of that for the end, it'd be nice to just get that sense of what did you have to overcome in order to make this work. But let's go with the number 9 upvote. As the number of individuals represented in available data sets grows globally, how do you handle relatedness and deduplication across data sets and biobanks?
This is a really good question, and it's something we're struggling in with GDI. We have a weird situation because you have a national, the data is basically in different countries. If you have individuals who are close to a border, they could actually access healthcare in either country. And this will increase in the EU as the prescription and the health records become more interoperable. And so it's something we do have to consider. I don't have a solution at the moment, so I can't answer it, but I can say we're aware of it within GDI because there are these edge cases where this could be an issue.
Soichi, you see there's a question coming for you. We're interested in your duo-enabled e-consent.
Yeah.
But I wondered, before you get to that, answering that specific question, perhaps you could also say, you talked about multiple biobanks in Japan. How do you handle this sense of relatedness and deduplication that you're not looking at the same individual in multiple biobanks and getting very excited you found a match?
Yeah, so it's very important question. So, yes, how to say, so I don't have any idea at this moment. So, yeah, so May I?
Yes.
Certainly.
If anybody else wants to weigh in on that other one.
So we are preparing the manuscript to represent our idea of the dual-enabled e-consent form. So that's I like to, how do I say? So you can see our publication, I think. So I hope we can do the collaboration in this topic. Yeah, thank you.
Okay. So I'll just say that in that question that people are asking about unique identities for individuals, it definitely came up at the IPCHIP meeting in Toronto on Saturday. It was one of the first questions that somebody new to the ecosystem said, what are you guys doing about this? I talked to colleagues in the US and they said, we got this solution that we're pushing hard to get that to address this issue, but only in the US. We don't know how that could possibly spread internationally. And clearly in rare disease, people could be seen in multiple countries, not just multiple states. So I think it's certainly been tagged for us recently as a piece of work that GA4GH could participate in. I'm not sure we should be the ones leading it, but it certainly is one that we should be partnering with others in that development. Let's go with, we're moving into an era where institution networks can self-publish their own data, enabling them to control their own access models. What role will national data infrastructures play in this brave new world, other than causing the panelists to come up in their seats so they can read the question? So we hear about trusted research environments, about secure data environments, we hear about national repositories. I think this is kind of pointing out that is one approach, but there are, given today's technology, everybody could decide to do it alone. So what do we see of those implications on national repositories of institutions and networks being able to publish themselves?
I can't speak for other countries, but I'll share experience in Canada at least. So Canada is actually a federation of provinces, and so with that perspective, it's actually a benefit to have federated architectures where each one of our provinces and organizations within a province can control their own clinical administrative data, but still surface their data in a way that allows for national insight. So in Canada, that model actually maps really well to the way our healthcare system is structured.
European colleagues?
Yeah, so in GDI, they're trying to harmonize the access model using the 1+MG framework. There will be some level of diversity at a national level, but to try and make this work across the whole of the EU, that's why we're having this governance framework effectively that will be the same across, or with minimal adaptations across the whole of the EU. So that's the only way really that GDI can actually work on this basis, we think.
Essentially, the idea is that we need to allow the countries to have their own interpretations of GDPR, to have their own national strategies mapped onto the way that they are sharing data, but we are trying to provide a central framework that's going to allow this to work. And so we are continuing to work at developing that, but we do need to allow the flexibility for countries to be able to do it the way they need to be doing it.
Okay. Rachel, I think so in many other countries, we see a national library, a national repository. That doesn't take place in the US, but you talked also about NCPI. So I think that sense of multiple repositories for important US data sets, but with similar rules, similar approaches, similar standards. So you just want to, I know you're coming at this from an AnVIL perspective, but just addressing that sense of a national repository, which isn't going to be one national repository in the US, but how it fits in with integration and federation.
Yeah, I think this is such a great question. Of course, in our era, we see more and more data becoming more and more siloed because of its value for institutions, for businesses. And so I really see national data infrastructures leading our advancement, our ability to continue publicly funded data and research in light of the way that data are now used kind of globally. But yeah, in the US, it's more of a collection of different funding models, different researchers, different environments. And maybe that speaks to the diverse nature of the research that's done, the disease areas, in a way that makes it more complex, but also expands the number of areas that research can be done, the ways it can be funded, while still charting that vision forward for maintaining that sense of publicly accessible research and results.
Yeah, I mean, you also have quite a different healthcare system from many other countries that are more centralized. I'm going to switch to the question that says, as multi-omics data are integrated into these data sets, that's cranked me up. Angela, can you just hold the screen up? We've moved it up to the top. Like proteomics, RNA sequence data, before and after diagnosis, repeat sampling. It will be important to understand in the context of genetic data. Do we have the ability to support such layered data sets?
Again, within GDI, we're considering this. So we're looking, GDI is only just starting, so we don't have the answers yet. But we are considering this in terms of longitudinal data and then linking this data for different data types. There's a whole range of EU-funded projects with not just genomic data, but other type of data that we want to be able to link and bring in so that you can, as a researcher within these different, what the EU terms as data spaces, which have a particular type of data within them, you can actually find relevant data across all these different data spaces and actually integrate it and perform improved research on the basis of that. But this is ongoing work we're doing.
Any other comments on this multi-data? I mean, I also hear that beyond multi-omics, we're seeing from cancer community, from neuroscience community, multimodal data and thinking about imaging being integrated with omics data. So there was one, we've got this one coming up. Can we go to the one that had 12 votes? Can you find that? Because it seemed like such a good one. There we go. Because it's for the GDI folks, and I am sure the rest of the world knows how good Europe is at sharing data globally. So can other people outside the EU join the network?
I mean, so as we're developing this, we are not trying to create a little European silo where we share with just ourselves and ignore everybody else. It's definitely not the goal. But I guess it depends on what you're considering joining the network. Joining the GDI project itself, it's a European Commission-run project, and so it is restricted to EU countries. However, we are making sure all of the outputs that we are creating from this in order to create this network are going to be published. I was talking about the 1+ million genome framework, and that is already public. So it's going to have very clear guidance on how to form a GDI node, and really any country, any organization can pick this up and understand how to connect up with it. And as we said before, it's all going to be based essentially on GA4GH standards with a few other standards put in there, but for the most part, it's based on GA4GH.
So, and I think we see that whether it's two organizations working together, saying we'll use GA4GH standards just to share between the two of them, or it's 4, or it's 10, or it's in a federated network. When we see these examples, we recognize that in order to get the humans organized to be able to use the standards, they need to have that trust and that common purpose. From our point of view, these are just more and more examples of great ways to implement. What we hope is that those implementations are willing to share lessons learned so that the rest of the world can benefit and not have to start right from the scratch. Which leads me to questions that have got 14 votes. Could each of the presenters speak to what the most difficult hurdle they had to get over in using the standards they based their work on? Who wants to go for it? It says all speakers. So there is no, this is not one where you can wait, hope somebody else says something really smart.
I can start it. I'm going to maybe bend my answer a little bit. I'll say that it's becoming exciting that organizations like Genome Canada is a funder and patient advocacy groups who really care about impact are hot on the adoption curve for GA4GH standards. What I would love to see is how we can either de-risk or incentivize folks that are not hottest on the adoption curve. So what do we need to do in order to get there? Can we build privacy-preserving machine learning technologies into these standards, or can we create new ideas around value attribution where you actually get incented to contribute? I think that would be a really exciting evolution of where we are now for us to drive more adopters. So it's not necessarily the standards that we have today, it's how we can evolve them to incentivize more sharing tomorrow.
Okay. From a GDI perspective, maybe you guys can come at it from two different perspectives. Melissa, talking about the not politics, we wouldn't think about politics, but the reality of a large, high-profile project in Europe adopting international standards, and then, Dylan, maybe if there's any technical issues, you could address it. So you get two answers.
I guess politically speaking, there's some pressure for us to not be over-reliant on GA4GH. And I think we are trying to show that GDI and Elixir in general in Europe is a major player in the driving of GA4GH standards and the adoption of GA4GH standards, and that helps to show the countries and the European Commission that it's not that we are relying on GA4GH so much as we are driving GA4GH and along with other countries, and if we want to be connecting up to the rest of the world, that it's important to be there. So we have to find the right political balance in that area.
Yes. So your funders, your principals wanting to see that you're contributing in, not just taking stuff off the shelf that somebody else did. Thank you. And Dylan, from a technical point of view?
Well, actually, yes, a slightly technical version of what Melissa's just said. So, for example, within Europe, they're developing an EID, which is self-certified identity, with an e-wallet. Now, effectively, this is very similar to a passport, and you control it. You don't have someone else minting it. They want us to use that for these data spaces I mentioned. So this is something that we're going to have to work with GA4GH. And one of the things more generally within the standards is that GA4GH was pioneering a lot of these things in terms of data sharing, but now the rest of the world is starting to catch up, and so we need to be able to look and see whether there's standards which are applicable to other, will extend whether the stuff that we've learned and can apply it to other data types and so on, so we have even more interoperability across these different standards.
Yeah, it's an interesting concept because our work streams, our leadership would have to look at that and say, so if somebody's made a better version, do we need to keep competing, or can we put our energy somewhere else and have that effect for everybody? Soichi, from a Japanese perspective, what are the biggest hurdles you've had in bringing these global standards?
Yes, so as I presented, so I'm working on the development of the biobank network, so just to implement the standards in the various biobank, so network connections. So at first, I need to share the visions and the issues, and we have so many discussions. So that's the human relationships and human connection is the most important thing to implement the standards, I think.
Yeah. Yeah. Artificial intelligence isn't the problem; it's human something. And Rachel.
Yeah, as I think back to the previous question, as we think about the ways in which the diversity of approaches, the diversity of data sets is such a strength, both in the context of the US, but also certainly as is demonstrated here in this community. The devil is also really in the details in terms of how you reach consensus on finding those harmonized approaches. And one thing that comes to mind that will resonate with lots of folks here is, there's a vision for a service that would issue passports for NIH data repositories that are part of the NCPI effort. And that is something we can all agree would be a fabulous path forward for data access, for researcher authentication, right? And yet the actual implementation of that service in all the different platforms and environments has been a very challenging path to move forward, right? And so it isn't for want of, agreeing with the vision, but I think really committing the effort that all of the teams have brought to the table for those types of real complex, challenging questions is rewarding, but is ultimately like the hard part.
Yeah. So in closing, I'd like to thank our panelists. We focused on real-world implementations, and I think if there's a takeaway for me, it's when you do this in the real world, all of a sudden, all those other factors come in. It's not just the technical specification, whether it works, whether it does the job in one setting. It's, are my partners using it? Will my funders accept it? Will my partners agree to all compromise, in their mind, compromise on something else? And certainly what we recognize is that GA4GH fulfills that third imperative and gets closer to healthcare. We have to work with other standards organizations. If we don't work with ISO, HL7, FHIR, etc., then there's no way these genomic standards can reach healthcare at scale. So I think your real-world examples have been great, and I thank you for your commitment to GA4GH. Now it's a network break, and I think we have half an hour for that. Thank you.
Thank you so much for your talk.
Thank you.
Hello, hello, everyone. We're going to try to get started. Even with a microphone, I am not very audible. Can we please sit down and start to get started? Hi. If everyone in the break wants to come take a seat, we're going to try to get started and stay on time, which is not typical for GA4GH meetings, but we are trying. Hello. Come on in, take a seat, please. Let's see. I think I'm also supposed to have a hand mic, is that right? It's not there. Probably. All right, are we ready? We're going to get started with our next session. In the spotlight, GA4GH technical standards and policies supporting broad and responsible use of genomic data. So to start, we have Jordi Rambla from the Center for Genomic Regulation in Spain. Thanks. I don't think I need it right now. But. All right, so Jordi is the team head at Center for Genomic Regulation. He is member of the Beacon team since the very first Beacon version, is currently responsible for the Elixir Beacon and Beacon network specifications. Jordi leads the Beacon API team, Elixir Beacon, and the EGA driver project, where he's a driver project champion, and he also contributes to several other GA4GH initiatives, including Discovery Workstream, Crypt4GH, HTS-GET, and RNA-GET. Jordi, over to you.
Thank you very much. First of all, excuse me because I'm quite nervous when I speak with this kind of audiences. Today I was requested to talk a little bit about the beacon and the Internet of Genomics, and you see that we put that in quotes because it's a kind of a concept. As Angela was kindly saying, I'm the head of the EGA team in Barcelona. We have two teams, one in Barcelona, one in Cambridge, and I'm part of this CRG. Starting with the EGA. The EGA is, so before that, I will give you or bring you through a short trip, a short journey, egocentric journey, I would say, because it's my experience, but I hope that at the end we will have a happy end, okay? So stay with me for these 10 minutes that I will be talking, if not over the time. So what is the EGA? The EGA is a project, a service that is archiving data, sensitive data from human biomedical research. It's a long name, okay? But the focus on the EGA is not on just getting the data inside a closet and use it just from time to time when someone needs this data. The idea is to foster the reuse, the responsible reuse of this data as much as possible, as broad as possible, so aligning with the name of this session. And this archive is co-managed by the EBI that was creating that in 2008, and the CRG that joined it in 2013, so now it's 10 years, like the Global Alliance. And actually, when I joined the EGA in 2013, little after that, I joined the Global Alliance and go to the first meeting in London, okay? And since then, I've been, I think, in all of them. So I joined the Beacon quite often, early. So the EGA is getting metadata and data from producers worldwide. And you see this pie chart is not the number of data we have, is the number of submitted accounts. Okay, so don't try to extrapolate anything from that. We can have much more data from Asia than actual submitters. It depends a lot on what type of indicator you are looking at. In this case, it's the number of people that sends data to us. And below you can see our recently born new submitter portal that was lighted last week. So the EGA has a model. We own nothing. We are just custodians of the data in the sense that we put them in the vault and we only open the door to part of this vault when the data controllers, the actual owners of the data, depending on how you see owners, but the actual controllers of the data tell us, open the door for this specific user account, okay? And then we do that, and our duty is to make the data sharing process smooth from the beginning to the end, let's say, okay? But in the case of the EGA, the access is all or nothing. If you request access to one data set from one DAC. The DAC says, yes, you have access, and then you have access to the whole data set, meaning the whole set of files, including genomics and phenotypic information we have. And these screenshots are from our DAC management system, the way of permissions, and all these kind of things. So after this model, what we had is a lot of diverse data. And this is one pie chart with the amount of files we have, what we call sequencing files. We have a total of 4,300 studies released. We have more in the pipeline, but these are the ones released. 10,000 data sets and 2,300 DACs. You can see that this is diverse, and we cannot do stuff as we like. It's a complex, heterogeneous ecosystem. We have more than 1 million FASTQs, 1.5 million BAMs and CRAMs, almost 1 million BCF, and let's say 500,000 array files. Okay, so it's a significant amount of data. So this is a successful model. We have lots of users, as you can see, lots of data, and it's simple, so it's successful. It's a combination of things. Both producers, data producers, and data consumers could be happy with that. So as we are in the business of data sharing, we joined the Global Alliance. It's easy peasy, okay? And we are supporting, there are several standards that are supporting us. You can read it in the screen, and we have a page where we describe which is the status of adoption of the different Global Alliance products that we look at in the ECA. And one thing that is interesting to us is these 3-layer access levels defined early in the Global Alliance history. And these 3 levels: public, meaning anonymous access; registered, meaning logged in, authenticated access; and control, meaning authorized access. Okay, so this is simplifying the model, and this was very attractive to us. And ECA lives in these 2 ends of this spectrum. We have metadata that it's public. You can consult it and read it and browse it in our website, but then we have lots of control data. And the fact that this is a pyramid, an inverted pyramid, is because this is an amount of people that has access to this kind of data. Okay, so given that we are in these 2 ends of the spectrum, and we have lots of interesting data that could be leveraged in different ways, we ask ourselves, how can we better service the community, leveraging the data we have, the knowledge we have? You can see I use the word knowledge here because we don't want to share the data. We want to leverage the data to share knowledge without disclosing any sensitive data. And it happens, as I was saying, in the first meeting I go with the Global Alliance, I discover the beacon, and I get in love with beacon, as you can imagine, okay? So this is a description of beacon B2, actually, but the concept is the same. You have an API where you ask a given data set, you have seen this mutation, this is in beacon B1. You have seen this mutation, and the beacon says yes or no. Okay? So this is the concept. The concept is you have Boolean answers, yes or no, and you have 2 objects, data sets and genomic variations. That's all. Okay? Simple model, simple API, easy to play with, easy to adopt. But then we have been contributing to that after, before Marc has talking, and Marc team has also been part of that. They have driven the beacon B1 with our help, but then we take the lead for beacon B2, and we end up with this solution. We have now much more objects, because one of the requests we had is give us context to the variant. Tell us if this is a man, is a woman, what type of disease, which age, which other conditions this user has, or this patient has, and so on. Okay, so we want that to be the context of the genomic variations, but they take life themselves. And then we add 2 more levels of answers, of responses. One is the count, meaning I can tell you not just if I have something or not, but how many I have. That could be much more interesting for you. If you have 1 single patient, let's say, then probably you are not interested in doing a meta-analysis of that. You can be interested if this is a patient you're looking for, but you necessarily are interested in doing a meta-analysis. And then we have another level that is, I can provide you with some details or all the details of that if you are authorized. Okay, so these are the 3 levels, again, with respect to this type of responses. This is not like it is. You can have all combinations of these 3 different levels, but 3 and 3, I mean. But for simplifying, we say Boolean is public and details is control. Okay. Okay. So I have a short demo of what we have, how we have applied this thing into the EGA. And this is a prototype. It looks much more than a prototype, but it's not. It's just a prototype, okay? So this is a user interface, and we are querying here the contents of the BCF in EGA, yeah? So I think that this was not playing, isn't it? So this was a video, but the video is not showing. Okay, so no problem. Can you show that, or we can do nothing? No? Okay, so, oh yes, now it's playing. Oh, wonderful. You will see, I'm logging in here first, I think so. Let me see. It's not moving now. Okay, sorry. Oh, now it's different. Okay. So, can we go back to the slides, or it wasn't my fault, maybe? No? He's trying to get it. Oh, thank you. Oh, yes, this is playing now. Okay, thank you. Thank you a lot. I'm logging in because I will query the data sets I'm having permissions to, okay? So I will query the whole BCF in EGA, but only the ones that I have access to. I look for a classical mutation, and I get the results in 1 or 2 seconds. Here they are. So we have 4,000 entries in our EGA that I have permissions to that have this mutation. And now we have added something more. What if we add the public things? Things like Nomad, things like CleanBar. And this is the query I'm doing here. I query this thing, and with liftover, and in this case we have no details for data set, but you can see we also have found 7,000 entries in these public data sets about this thing. This, let's go. No, it's my fault. I did changes last minute. So this is the karma punishing me. Yes. Okay. Yeah, okay. So this is what we have. Just this 1 million BCF is giving us this number, 150,000 billion entries. And you have been the response time we have. And the technology behind that is super simple. It's just a BET file with a B3 on top, B3 index on top of it, yeah? And we have been doing that in a laptop. And if we add the public data, oh, now it's going a little bit slow. Maybe I'm clicking too much. Oh, it's destroying the effect. But when you see the results of this thing, yes, this is the public data. You see the kind of data sets we have added there. This is 500 billion, more than 500 billion data. And you have seen the response time. This beacon is not tweaked this video is not tweaked at any way. This is the exact response time we had for this thing, yeah? And you see the comparison of what we have in the EGA BCF versus the size of one thing versus the other, okay? So now we have a beacon that is able to give you answers for this whole set of public data sets plus the EGA BCF if you have permissions to, in matter of seconds, and then you can move forward with it. Okay, so how is this related to Internet of Genomics? This is related in one way. In one side, I show you one centralized approach. We move everything into one single place and you query it. Okay, good. But we have also a federated approach. And this is a short story of how we applied beacon in different places, how we are applying beacon in different places. This is one Teleton project for some hospitals in Barcelona, just in Barcelona. This is a map of Barcelona with some of the main hospitals in Barcelona. And they want to do a beacon network among them in order to share information about the patients they have seen in these hospitals. This is an example. Then this has been a little bit popular, and we have now 16 hospitals around Catalonia, that is the country, the state where Barcelona is. And you see the main cities in the region also joining the project. So we have something local, something private, let's say, that is using beacon for genomic diagnosis. This network is part of a bigger network, could be part of a network, to be honest. In another project that is called Impact Data, fostered by the Ministry of Science in Spain, that is using these hospitals and other hospitals in order to have a local network, a national network. And in this case, together with the BSC, the Barcelona Supercomputing Center, we have light a beacon on top of a mop. So instead of having another backend, what we did is put a beacon OMOP CDM in Postgres and put a beacon layer on top of that. So now you can query beacon and get results from OMOP. Okay? And this network could be part of a continental network. Dylan and Melanie have explained you about GDI. So you here have GDI. There is also another initiative they call the Federated Genome Archive, European Genome Phenome Archive, the FEGA, that is also having a beacon network on top of it. But also one another of the new driver projects, Ears for Cancer, we are starting to create a beacon for cancer registries, a beacon network for cancer registries using the model of the European Network of Cancer Registries. Okay? So you see that we are growing from something that is local to something that becomes more and more and more global. And last but not least, it's not just Europe. In Africa, there is a plan for lighting a network of beacons across Africa. Okay? So if you join all these things together, we can have of an eventual global beacon network. Yeah? And this is kind of the Internet of Genomics. Okay? So are we succeeding in this thing? Are we succeeding in the Internet of Genomics? I would say it's too soon to say. Most of these projects are ongoing. There is lots of billion people working on that and some funding. Not that much funding as people, but we have some funding. And people from different origins and backgrounds, from clinicians to geneticists to bioinformatics in the hospitals to technicians, like I consider myself mostly, and other kinds of people, okay? So if we don't succeed now, I think it will be hard to succeed in any other occasion because we have a big opportunity right now. Lots of sensitivity about that, lots of power on this, and lots of good tools for that, okay? So I hope we will end up succeeding, but it's too soon to say. So then, this is a summary of my journey. As you can see, the end is kind of happy, not necessarily done yet, but kind of happy. And also, I will like you to, if you are so kind to answer our EGA user survey, I will appreciate that, my team too. So thank you for your time and your patience with me, and see you now. Yeah.
How about if I turn it on? Does that work? Great, thanks. All right, thank you, Jordi. That was fabulous. I loved being on that journey with you. So there was recently a paper from CSIRO about a serverless beacon. Are you familiar with this? And is the beacon workstream considering working with the group?
Yeah, I'm somewhat familiar with this project. They have done a presentation some time ago in the Global Alliance Beacon Working Group. I think that it's very nice. They have an implementation that it's meant for production. So this is good, and it's another implementation. Others probably are not that mature like that one. So it's a good thing, and I encourage you to look at it if you are interested in having a production beacon. We have other options like the one I showed right now, that it's a pilot from EGA, but it's to demonstrate that the simple technology, simple solution could bring you results also, okay?
So the next one is just clarifying, when you talk about diverse data, are you talking about diversity of formats rather than the data, the types of...
It's diverse in many different ways.
Yeah.
So today, when I was looking at the fetal presentation this morning, I was looking to fetal data in EGA, and we have lots of different things, from RNA-seq to sequencing to many different things, okay? So it's diverse in many different ways, yes.
And we'll try to take these two quickly. We're a bit over, but I don't want to cut you off. What are the next steps for EGA Beacon version 2 prototype?
In the case of the EGA 1, is making it, as you have not noticed that, but for example, in the public datasets, we only have a summary of it. It's not telling you which public datasets are having this data. Or when we show the data from the EGA, we only show you which dataset is in. So this is just a prototype. It's for us to show that it scales. We have done tests with 10 times this amount of information to see it scales, and that we can look and I don't remember the word in English, but we can found the data associated with this one, because this beacon is not having the data set. You need to look for the data sets and so on. So you have lookups. That's the word I was looking for. We need to do some lookups, and we need to improve that thing.
All right, last one, and then if anybody has additional questions, you can keep putting them on Slido or bring them to the Slack. Are you, oh no, last one more, you've got one
the
more.
last one, okay.
Are you working with the Beacon implementers? Is there follow-up or discussion?
Yes, we are working a lot with that, both in the context of the Global Alliance and also in the context of Elixir. All these projects that I mentioned, we are involved in that. That's one of the reasons I said that we have funding, but not probably enough funding, because my team is working a lot on that and other projects that are not our projects indeed, okay? So yes, we are involved with implementations a lot, let's say.
Awesome. Yeah, and I think if that person is interested, like join the Beacon meetings, and you know, we've got resources for you. Thanks so much, Jordi.
Okay, thank you.
And now we will move on. All right, so now we have variation representation standard with Larry Babb. Larry is a senior principal software engineer at Broad Institute. He's spent 30 years designing and developing data models, software, and tooling, with the past 15 focused primarily on managing and sharing genetic data to improve clinical care. He leads and contributes to grant work involved in cross-organization systems design, development, and data sharing standards to advance computational reliability of genetics knowledge for use in clinical practice, and he co-leads the VERSE product team and contributes in so many ways at GA4GH. Thanks, Larry.
All right, thank you. So I have to first say that usually this is the Alex and Larry show, and Alex couldn't make it this year. He had a medical thing right before this, and he's doing fine and all that kind of thing. And I'm much more nervous when Alex isn't here, but I found a solution to bring him. And so Alex is here in spirit. I want everyone to know that. And this actually comforts me more than I think it should, but so I'll just put him there for a second. You know, we'll figure that out. But all right, so anyway, let's get started here. I'm going to see the slides down here, right? Oh, that is the slides, right? So next slide. Oh, I do it. Geez, that's good. Green button. Here we go. Is it which green button? There's a big green button. Okay, there you go. All right. So I'm doing this really on behalf of Alex. Alex helped me immensely with this. In fact, I'd say honestly, he did this presentation. Alex is a PhD and a very smart individual and actually a really great engineer. I'm an engineer, or I used to be, and I do a lot of management now. So I'm going to try to channel Alex, and I apologize if I say something really awful, but and get it really wrong, but please bear with me. So my job here today is to take you through what we've been doing in VERSE in the last year, and I'm going to go through and try to explain that, and these are the sort of the points we're going to go through. I'll bring them up as we go through them. So first of all, you want to know why do you care about genomic knowledge standards? So for those of you that aren't in the weeds with us, Alex put together these 3 lovely statements and explained them to me, and now I'm going to try to explain them back to you. All right, so the first one up top is pretty simple. Huntington's disease is fully penetrant with patients that have this polymorphic trinucleotide that has a repeat count of greater than or equal to 40. And this is a well-known, so I'm told, this is a well-known ACMG guide for clinical laboratories. And this is a pretty simple thing to deal with. And if you look down at the bottom at the legend, what you'll see is a little bit of a cheat sheet of what we're doing in standards to sort of carve out the subjects, the objects, the predicates of these statements, and the qualifiers. And we'll get to that as we get to the end of this. But not every statement is that simple. And so you have, let's take this second one, and here we go. So the multiplex assay variant effect experiments have variants that show, have these variant functional impact statements. And here's a variant from an experiment with P.I5Y that has a loss of function score. And it just so happens that they've been able to map that to a SCNA5 variant in the human genome that has uncertain significance for Brugada syndrome. So this kind of experimental variant score actually can support the potential pathogenicity of this mapped human variant. And this is the kind of thing that is a lot more complex and nuanced, but yet we want to be able to keep this kind of structure so that when we're looking at how people assess variants, we can see exactly how they came about it. So this third one is an interesting case, I guess, is the BCR-ABL1 fusion that has with it a T315I mutation. And this is apparently a well-known, well-observed or variant that confers resistance for imatinib. And it does it in the context of CML. And the interesting thing here is that with the other statements, you know, and I come from the rare disease side, the disease is usually the object of these causal statements. But in this case, CML is more of a qualifier. And the true statement is really that this variant confers resistance in this drug in the context of CML. So we've been working for a long time with this, and I got to say, we need computers to be able to understand this. So how do we help with that? And that's what GKS is really about. So GKS is really made up of three primary areas. The variant representation area, which is really about the vocabulary and describing variation itself. The variant annotation area, which is really about building a framework to integrate this knowledge and evidence that we saw on the last slide. And the sequence annotation group, which is really also building a vocabulary for annotating sequence features. Today, we're here to talk about the variant representation work that's gone on in the last year. As some of you may know, and some of you may not, back in 2021, we published the VERSE spec, the Variation Representation Specification. And if anyone's interested, you can go out to verse.ga4gh.org and look it up. And in there, you can see, for those that want to read more about it, there's a citation there, a link to the cell genomics paper we published that year. So what have we done in 1.3? And earlier this year, in April, we released 1.3 of VERSE. And what we did is we added 3 new variation types, as you can see. We improved our representation of copy number. And we have 2 kinds. In the first, on the left-hand side, we see the copy number count, which is really about measuring and representing copy numbers when you know the absolute or ranged amounts of copies. So you can see there on the left that you can have 2, 3, 4 copies in that particular graph. So this is about really absolute copies, copy number counts. And so we created a class for that. But there are some groups, and I've been told that particularly in somatic or in cancer variations, they run tests where they produce these log-fold value experiments that measure whether CNV is lower or higher amplitude. And those would correlate to copy number losses and gains. That's my understanding. So I've seen plenty of this data. I didn't know that's how they did it, but that's really interesting. In any case, we created a copy number change to represent those data type too. And finally, we put together the genotype, finally got together the genotype class that we've been chasing for a long time back in April. And this is nice because it built on top of our allele and haplotype classes that were already in VERSE. And there's a paper out there on this as well, or there's certainly a reference that you can go look that up. Okay, so now let's talk about how we're applying it. We're going into the second step of how we're applying VERSE 1.3 at scale. So as we speak, we've been working with Nomad. Actually, for a little while here, Alex Wagner got a grant to work with the Nomad team. So Heidi's Nomad team and Alex's team and a little bit of myself and Kyle and a few others got together to actually apply VERSE to Nomad. And what we've done is we've been able to versify the 759.3 million variants in Nomad 3 in the HALE tables itself. And if you really look at that with the reference alleles, that creates 1.5 billion VERSE alleles in total. And this is now searchable by range and computed identifier in HALE. I say now like you can run out and do this, but really there's a public set right now out there that's a set of 100,000 randomly picked ones that we used as our test set. And we are in the course of about to release version 3. And I can't give you a date, whether it's going to be next week or next month, but it'll be soon. In any case, you'll be able to access these tables and go after this with the HALE function that you're seeing here in a Jupyter notebook. And down below, you're seeing in the middle column what those VERSE IDs are, and including the VERSE stats, starts and ends and states. So if you take all those columns from the second one over past where it starts with VERSE allele IDs, that really is the structure of the VERSE object itself. So anybody should be able to go out and get that. there's some additional work being done to also bring back the NOMAD data in a VA form for like a population allele frequency study result. And that hopefully will be coming out in the next month or two as well. All right, on to another very interesting project that Alex Wagner's team worked with the MaveDB team, and we have Alan Rubin over here who's been trying to brief me on how to properly represent this. So what this multiplex assay variant effect database does is they basically have this huge library of experimental variants from these organisms that they run these high throughput functional assays on to develop these score sets. And the challenge there is we want to use that data as evidence to help map it to the human variant, because it's not always a one-for-one or identical kind of liftover kind of thing, is my understanding. So what they've done is they've actually created the mapping using verse identifiers so that we keep the true identifier of the experimental variant side by side mapped to the variant that you see in the human genome. And this allows you to see the power of verse. And I would defer you to Alan Rubin to really tell you how wonderful this is. He seems really excited about it, so I trust it's very good. And I know Alex is very excited about it. So anyway, we'll go on from here. This is what if you go out and look up a particular data set or data group or whatever in MaveDB, down below you'll see, and this is available today, the Map to Variants button, and you're welcome to go out and hit that, and you can see this. You'll see a whole set of data related to this particular group experiment that will show you the mapping between the human and the experimental variant, and you'll have that true provenance held within it. And it sounds like it's fairly groundbreaking. Is that 19 seconds? Is that really down to that, huh? Okay. All right. On to the GK pilot. Last year, we introduced the GK pilot version 1 in I can't stop looking at that now. All right, at the 10th Plenary in Barcelona, and basically what we did is we went out to ClinVar and Civic with the Vic and ClinGen driver project teams, and we took an excerpt and we turned it into the VA specification. That was all built on verse 1.2. What we actually have done in the last 6 months is we've been working so hard on this to get the GK pilot version 2 enhancement going. We've now moved to a verse 2.0 alpha model. And verse 2.0 is the next generation, so it's going to break the identifiers from 1x. And that's sort of disappointing, but we learned a lot of stuff over the last year. And one is that we learned that we can actually make this thing simpler to build and more performant. So we've done a lot of that work in the alpha phase of this verse 2.0, and we've built this new GK pilot that is now out there in the GA4GH Git repo in the GK-pilot repository. And I'm going to be cleaning that up so it's a little easier for you guys to see it, and I'll send out a link afterwards on these slides. But anyway, it's more compact, it's self-descriptive, it's flattened, it's got a whole bunch of really great stuff. I'm just going to go on and tell you that it's much better than the 1.0 version. So, all right, and we are piloting the new maturity model. This is something we realize in GA4GH that we think other groups need, and so we're sort of taking the leap of trying this out ourselves, which is to make sure we, as we build stuff, we make it available as we build it. And I'm going to sort of end on a note that it was about 5 or 6 years ago that I got to go to, I think it was my first Connect meeting, and Ewan Burney was, I think, probably not new maybe, but I was in the Connect meeting in the audience, and he got up there and he was trying to motivate all the working groups and whatnot to get stuff done, and he basically said, rough consensus running code, because, you know, times we can get in the rooms and there's a lot of palaver and not a lot of progress is made. You know, it's made on the whiteboard maybe, but not in reality. So we took that to heart in this last year, and we've been doing it. So in honor of that, we came out with verse 2.0 here. I don't know if you can see it. It's got Ewan's thing down there, but that's basically what we're doing. So our rough consensus running code alpha version is ready, and we've been doing a lot of work in the last 2 days to move it on. So I will finally end with that we have a structural variant special interest group that's been working with Daniel Cameron to add structural variation to 2.0 alpha. This is very active, and Daniel Cameron's doing a wonderful job along with Myrnal Thomas from Epic. And we have Daniel Puthawala, we're going to propose a study group for getting into categorical variation, which I do not have time to get into right now. And I want to let you know, if you're interested in helping us with any of this, contact Beatrice Amos. She's the best coordinator, manager we've ever had. So, yeah, in any project, in any group. So there you go. And this is the group we did, and I gotta say that one of my co-leads, Andreas Prelig, is not on here, and I am so embarrassed because I did this like 2 minutes before. All right, that's it.
Thank you, Larry. That was great. Are you also embarrassed because Melissa Konopko's in the audience, who is also a coordinator for the GKS?
Yeah. There's going to be a lot of that. You know, I might not be back. Next year you'll see a head of me, but not me, probably.
All right, Larry, so we don't have a lot of time for questions.
That's where you go.
We don't have a lot of time for questions because...
All right, I did
but
it.
No, don't go. We want to do at least one. And then the rest can go on Slack. So for Nomad's implementation of verse-based search, were they able to just use their existing database search with a few new columns, or did it need custom code? And what does that say about the cost of other systems doing the same thing?
Hey, Kyle, for Nomad's implementation of verse-based search, so I believe what they did is we just built a function within Hail, and the Nomad methods team has their own functions that are built around their Hail table that they produce. So we did build code, and yes, they had to put new annotations in the VCF files that essentially get put into Hail, if you know how Hail works, and it basically just uses those coordinates and stuff to do the search. So I guess it really did add new columns, but that's how, whenever you have new data, you have to do it, right? I'm not sure I understand how else you would do it. Yeah, it was just those ones you saw. That was it. Yeah. Yeah.
When should we adopt which updated version of Verse in Beacon v2n? I don't understand that one.
Yes, you should adopt Verse in Beacon v2 for v2. Which one? I would say. I would say 2.0 beta, which will be coming out hopefully well before Connect next year. So at Connect next year, we should have some serious conversations about that. All right.
Thank you,
Thanks.
Larry, and Alex.
Yep.
So can we get the screen back? Thank you. Okay, so now we have a tag team with Nathan Sheffield and Andy Yates. Nathan is associate professor, sorry, I looked that up, but it's not in your bio, at the University of Virginia, where his lab studies computational biology, I guess. And he also was a postdoctoral fellow in Christoph Bach's lab at the Center for Molecular Medicine in Vienna, and a return phase of his fellowship with the Howard Chang's lab at Stanford. Andy Yates is a team lead at AnVIL EBI, where he coordinates interface development, data access, APIs, production support, outreach, and training for Ensemble and Ensemble genomes. And he also co-leads the Genomic Knowledge Workstream for GA4GH. He's involved with a lot of stuff. So please welcome them both.
I want to start off with a couple of things. First, all workstream managers are awesome. Okay, and it's a real privilege to be talking here, and it's a real first as well. I have never spoken in front of an audience with a massive gold peacock in the same room. And if anyone's wondering where it is, I swear, once you find it, you'll be amazed that you ever missed it. So we're here today to actually talk about two standards. Well, I should say one is a VETAS standard that was originally approved in 2018. We've had a refresh, that is refget, and also an emerging standard as well, which we hope to be pushing through next year, sequence collections. Now, I want to start off with three problems that we're trying to solve here. One is around specificity, a second is around validation, and the third is around interoperability. I do apologize about the stock images that are used here. I recently got burnt off not using stock imagery, so I'm not making that mistake again and didn't want to pay the money for anything else. But effectively, if you keep remembering these three topics, they will keep on coming up all the way through the talk. So the first, which genome did you use? Now, Jordi's talk was absolutely fantastic because we had an interface that just said GRCH37. We refer to genomes through these colloquial names, HG38, HG19, GRCH38. Those names can also be interchangeable. Now, the thing is, though, that when someone is actually performing analysis on these genomes, they could actually start to modify those sets. And there's a ton of different things they could be doing. They could be putting in decoy sequences in there. They could be introducing EBV. They could be excluding the pseudo-autosomal regions. They could be including them. They could be changing the names of the sequences that they're using. And I didn't want to just I just want to underline how challenging this can be by a random publication that I just typed in GA4GH 38 into Europe PMC, and you can see that actually they refer to HG19 and GA4GH 38, and there's no link to actually what that means beyond just those genomes. So we are left to interpret what potentially happened there as well. This isn't a huge barrier. We've been getting along quite nicely without actually being a bit more specific about this, but it is a potential source of problems which could impact data exchange and sharing. The second is also validation. How can you assert a claimed genome? Where did that genome originally come from? There are a myriad of different providers available who will all say that they provide the exact same genome. I'm actually from one of those, the Ensemble project. There are other providers displayed up here. And each provider may change some of those sequences as well. This is a little known fact, but there are definitely changes that have happened to the sequence content behind some of those genomes as well, but they remain coordinate system compatible with each other as well. And the similar problems existing with the naming conventions assigned to that as well. Here are 4 names assigned. They all mean the same chromosome. Chromosome 1, but they're all different. And if you're presented with a file that has one of those items, how can you actually interrupt between those? So effectively, how can you actually assert that identity and integrity of the data that you're trying to process? And the final one leads us to interoperability. The use of alternative names is sometimes enough to actually stop you from integrating. Being from the Ensemble project and working a lot with the UCSC genome browser as well, we know one of the main problems there is the addition and removal of CHR from the names. And of course, someone turns up quite nicely, goes, oh, slap CHR on the front of it. That will fail. Absolutely 100%, that will fail. It will work for the most part, you'll be fine, and eventually when it fails, you'll be like, oh, why did that happen? There are other alternatives around that. Have conversion files, have mapping files that are available for that. Those issues are only seen, though, normally when the systems start to fail later on. And I did think it's probably a very 2022 here. I just slapped into ChatGPT 3.5 because I'm not paying for ChatGPT 4. What the major challenge is, data standardization basically came up, and it said exactly what is going on here with the problems. Platforms use different naming conventions, use units of measurement, and standardization is absolutely key to this. So great, it's actually learned exactly what's going on there. Go AI. So where do we fit into this? The refget suite of standards provides the ability to perform those 3 operations over sequences and over collections of sequences. refget v2, which was approved in July 2023, this is an existing GA4GH standard, and this is applied over the top of primarily genomic sequences over chromosomes, and produces identifiers based on sequence content. It also provides an API for retrieval of that. In the version 2, one of the major changes we did is that we actually switched to be able to retrieve sequences through the use of common identifiers that are unique. So where we had things like the CM identifier there, that would actually be a valid identifier now to retrieve sequence. So this is solving one of the major problems we had from V1, which was I need a unique identifier that you've generated, but you need to know what that unique identifier was in the first place. So this is kind of bridge that gap. The other side of it is sequence collections, which is a developing standard and is applying the same ideas that came along for refget and to build that to other types of collections such as proteomes, transcriptomes, and pangenomes. It also adds in a few extra functions, and at that point, I am going to pass over to Nathan, who will take you through sequence collections. Yeah.
Okay, thanks, Andy. So Andy did a great job of describing some of the problems. So I'm going to, in just a few minutes, try to explain how we actually are doing these standards, and hopefully you can see how they can at least start to address some of these problems that we've talked about. So these standards, refget and sequence collections, there's 3 components that I wanted to talk about, and just a slide or two on each of these. The first is identification, So how are we using this to identify sequences and collections of sequences? Second, retrieval. So what's the standard that enables us to be able to retrieve a sequence or a collection of sequences, given that you have its identifier? And then finally, specifically for sequence collections, how do we compare among two sequence collections to try to get this question of, if we did analyses on slightly different versions of the human genome, well, for some things we might require strict identity, but for some things it's okay if we're just coordinate system compatible. And so how are we going to do that? So we'll get to that in comparison. So first, identification. How can we be more specific? So this is all based on this idea of creating a content-derived identifier. So that's an identifier that is derived from the content of the thing that it identifies. The beauty of that is that it enables us to build a federated system because we don't rely on some kind of a centralized authority to sort of mint an identifier and say this is what this is. But everybody can compute whatever they, on whatever sequences they have and arrive at the same result, and so we can have a federated system. So the basic idea is that you take your content, whether it be a sequence, a collection of sequences, what have you, you extract key features, key attributes of that data. Those are the things that you think are inherent to the definition of that object. And then we're going to run a cryptographic checksum algorithm, so MD5, SHA-512, or some variation on it like we do in GA4GH. And then out comes this string, and that's sort of a fingerprint or a barcode or an identifier. So that's what we would call a content-derived identifier. So in refget for sequences and for collections, we basically use this process. So I'm showing you here on the upper left. In blue, we have a sequence. We run this kind of algorithm. We get an identifier. So that's the unique fingerprint for that sequence. And then sequence collections inherits from that. And we wrap those identifiers together with their names into a collection of sequences, which we then use to create an identifier for a sequence collection. So sequence collection builds on refget. So we use the refget identifiers in the construction of the sequence collection identifier. So, and sequence collection identifiers, like refget identifiers, are also content derived. So how to compute a sequence collection identifier? We've got a little slide up here, and this is several years of discussions and implementations, and I can't really do it justice in a minute. But these are the steps. Essentially, you create a canonical representation of these sequences, which includes their lengths and their names and the identifiers of the sequences. We use an external standard, RFC 8785, which is a JSON canonicalization standard to apply to each one of those attributes, creating a standard string representation of that data. We then digest each one of those strings according to the GA4GH digest algorithm, and that's where we are at step 3. And then we essentially repeat that process one more time. So we take that object, canonicalize it into a canonical string. So this is eliminating any sort of like white space issues, and then digest it again with the same algorithm. And that's how we end up with the final sequence collection identifier. So the hope is that you could use that in your publication instead of saying GRCH38. You'd say we aligned to, you could still say GRCH38, but you'd say GRCH38, this identifier, right? And then now you're uniquely identifying exactly the thing that you used for that analysis. So the last thing is, this is the second thing of 3, the retrieval. So you want to be able to retrieve those once you have them. So this is this pretty simple API for refget. There's a sequence endpoint. You give it a sequence identifier, you get back the sequence. For the collection endpoint, it's similar. We have a collection endpoint. You give it a collection identifier, you get back this specific collection, which includes the refget identifiers, so you could go back and get the actual sequences if you needed them. And then the comparison endpoint. So for sequence collections, we have specified this ability to compare 2 collections of sequences. So you just give 2 sequence collection identifiers, and you get back a response that looks like this. It tells you information about which attributes are present on which of those sequences, and how many of those elements matched, and how many of them matched and were in the same order. And so this is not intended to be a human-readable response, but from this, you can assess all kinds of different sort of compatibility questions. Besides just strict identity, are these the same, which you can get from just looking at the, do the identifiers match? We can ask, are these the same sequences but just in different order? We can ask, are these the same underlying sequence content but with different names? We can ask, are these length only compatible? So I don't necessarily care about the actual underlying sequence content, but do my names and lengths match? Is that a matching coordinate system? So from this information, you can answer all of those questions sort of programmatically. So I'll turn it back to Andy for the last slide or two.
Okay, yeah. So in terms of what's available, a refget, there is the CRAM reference registry, which is the primary original implementation of this. That supports CRAM, so if you use CRAM at all, you're using the CRAM reference registry under the hood. That shipped 70 terabytes of data in the past up until this point this year. Ensemble is going to release its own version of refget as well, which will provide access to transcripts and to proteins as well that are being annotated. And that also includes ones from the HPRC project, so you'll be able to get access to pretty much any kind of transcript that you want. There's also the specification available in the tools. Sequence collection is going through this draft phase at the moment. There are reference implementations available behind that. There's also commitment from EVA and also from Ensemble at EBI that we would look at putting up versions of this to provide sequence collections over the genomes that we actually process and use. So in summary, both of these standards allow you to help you to unambiguously specify reference data for your analysis. You can also use them to validate data using these computed identifiers, which are devoid of the central issuing authority. And also, sequence collections allow you to assert the interoperability between these methods. And these methods can actually expand beyond just genomes due to the really broad applicability. And with that, thank you very much. Very sorry about the time. That's my fault.
Hello. Don't worry about the time. We had Ewan down for a 15-minute presentation at the end of this, but
cool.
That's not happening. Don't worry. So we have more time than we realized.
I would like to take this first one. What do we mean by coordinate system compatible? Okay, so coordinate system compatible would mean that the sequence content is different. So say the redundant ambiguous positions within that chromosome were replaced with just ends, but the length was the same and the name used was the same. So that would effectively be operating within the same coordinate system. So that's what we meant by coordinate system compatible.
Can we take, is it part of the roadmap to include graph genomes to your specification amongst others to support the new pangenome driver project?
Yes, absolutely. Am I all right taking that one?
Sure.
Cool. Okay. Yes. So actually, one of the nice ideas behind the sequence collection specification is that we can actually derive additional collections based on collections of collections, because it just recurses. One of the ideas that we have both been talking about is, could we generate a pangenome sequence collection based on the pangenomes from HPRC and, of course, from HPP? We have actually done that. Nathan has been spending the past few days generating those checksums, generating those sequence collections. We haven't got around to actually doing that next stage yet of generating that next stage of here's a pangenome sequence collection, but it is definitely possible, and then that would allow you to actually identify, hey, these are all the genomes that actually form into a graph data structure representation, and therefore when the thing that is going to be really obvious in the pangenome world is that there are going to be very tuned pangenomes out there, different types of graph representations based on similar types of data. So knowing the composition of those graphs is going to be incredibly important and actually broadly applicable to other areas of life as well with the other with other graph genome and pangenome projects such as in crops and in food security.
All right, next one. How complex is it to follow the steps to generate an identifier? Are people likely to get it wrong and come up with the wrong ID?
I can answer
or a
that,
different
yeah.
ID?
Yeah, it's, so we have a Python implementation. So one possibility is you could just use that Python function. You could probably write it in, 10 or 12 lines of code. But maybe more importantly than that is that we can provide, examples so that you could sort of test, right? And so I think that if you were going to come up with your own implementation, basically you'd run this test suite to make sure that your implementation is actually minting the same identifiers that all the other implementations are. But presumably there will be multiple implementations in multiple different languages, and so you could possibly just grab one off the shelf, or it's easy enough that you could probably just implement it.
All right, I'm going to take one more question and then we'll put the rest on Slack. How do you resolve sequences from repetitive regions, transposons, et cetera?
So for us, we don't have any knowledge or sequence collections, and refget don't really care about the annotation or what the sequences are. These could be, I mean, you could put sentences in there if you wanted to. I mean, you can put proteomes in there, you can put transcriptomes. So to refget, a sequence is just a sequence of characters. There's no sort of annotation or information or alignment or anything like this. So if there's repetition in there, fine, right? We're just taking the sequence as it comes and digesting it. So the concept of transposons and repetition are sort of not relevant in the concept in the concept of refget and sequence collections.
Thank you. We've had this one around for a while, and I feel like I finally might be getting to understand it. And thank you. It's really an incredible piece of work. All right, and last but not least, return of secondary findings in pediatric pharmacogenomics. I don't need two Nikes. Vasiliki Rahimzadeh. Dr. Rahimzadeh is faculty at the Center for Medical Ethics and Health Policy at Baylor College of Medicine, where she investigates the ethical, legal, and social issues of health data sharing across emerging computing environments. The goals of her current NIH-funded research are to inform data governance, policy, and practice, which maximizes the scientific value of health data and respects the rights and interests of individuals and communities. She's been an active RUSE member since its founding and currently co-chairs the DACRES and Ethical Provenance Working Groups. Thanks, Vaso.
Let me get us set up here. Thank you so much. So on behalf of the co-authors and members of a special interest group in pediatrics, we're really thankful and very grateful to the organizers for the opportunity to feature this work that's been ongoing for many years and even survived a pandemic. And these are the development of a set of points to consider for the ethical return of secondary findings in pharmacogenomics involving children. Big green, yes. Nice. So I'm representing this work today and ideas from a great many collaborators that were fiercely led principally by Jan Friedman from the University of British Columbia. And so the purpose of our white paper and what I'll be discussing today is to review considerations that are important for clinicians and policymakers for deciding whether and under what circumstances to screen for pharmacogenomic variants in children that are unrelated to the initial indications for which whole genome or exome sequencing was indicated. And in this paper, we use pharmacogenetic testing to refer to a method for defining the genotype of one particular gene or genetic locus, and pharmacogenomic tests to assess genotypes at many loci throughout the genome simultaneously. And so this slide is just to give you a sense of the many years and efforts that contributed to this final working in white paper. And I think it's testament also to the enduring nature and the ethical import of this topic to really the delivery and acceleration of genomic medicine in precision pediatrics in particular. And I think before we get too far into the policy development, I think it's important for you all to know what was excluded from our discussions. So we did not discuss the return of other kinds of secondary findings, such as hereditary cancers or cardiac conditions, nor do we discuss the intentional screening for pharmacogenomic variants in the general pediatric population, as might be part of a newborn screening program. And we also didn't consider clinical testing of individual children who are undergoing treatment for which the pharmacogenetic testing was indicated. And so I think, as is well recognized within this community, we know that establishing a causal diagnosis in a patient with a suspected genetic disease is really essential for clinical management, and that frequencies of inherited variants really differ across healthy populations, in part and as a result of diverse genetic ancestry. This also holds true for actionable pharmacogenomic variant alleles, but as we know, whole genome and exome sequencing not only identifies genetic variants that we're looking for in our disease causing, but also variants at almost any other genetic loci. And so this can reveal those variants that are unrelated for what we were looking for, what the physician was ordered in the first place. So this really results in what practitioners in the field called secondary or incidental findings, which can have important medical, personal, or reproductive implications for individuals who are tested, as well as their biological relatives. Many policies have therefore been developed for the return of these results to patients and families, but they differ significantly by jurisdiction and by healthcare system. So clinical laboratories in the United States, for example, follow the ACMG recommendations to report secondary findings in a particular set of genes whenever sequencing is performed, unless a patient or their family requests not to do so. In contrast, the Canadian College of Medical Geneticists and the European Society for Human Genetics do not recommend intentional screening for variants in genes unrelated to the clinical indication for diagnostic testing, and this includes pharmacogenomic secondary findings, except in two cases, in the context of pilot or research studies that are trying to determine the clinical value of return of those results, or when those results imply a significant high risk or highly penetrant condition that's medically actionable during childhood. And the during childhood point is quite significant. So these are just a few examples. Yeah. These are just a few examples of the variability that exists in the policy, and so our working group was really compelled to work on the issue of return because children are at particularly high risk of serious adverse drug reactions that could be mitigated if this testing might be performed. And so in the paper, we elaborate in detail some of these systemic, scientific, and ethical challenges for the return that you see listed here. So among those, the fact that there's very limited consensus on who has the ethical responsibility and professional obligation to preemptively test for those indications. There are issues with respect to consent, including data privacy and storage of that data, as well as incorporation into the electronic medical record, just to give a sense of a few issues that we elaborate in further detail, but that are significant to this work. And so taking all these issues into account, I'm going to very rapidly take you through these 10 policy points to consider that we synthesized. And they're based on this foundational premise that the best interests of children remain the primary consideration for the return of these results, that all policies that address the return of results must cohere with existing policies, guidelines, regulations that are relevant in the jurisdictions from which this testing is performed, that laboratories have specific reporting obligations in this whole enterprise, namely in reporting aggregate reference and variant allele frequencies, and that make these data accessible according to the FAIR principles in existing databases or data repositories. If a policy is drafted or created that enables return, it has to apply in the same way across all patients who undergo testing and apply to their families as a point of equity. So we acknowledge the diversity across healthcare systems, particularly in under-resourced settings. So this policy has to equitably apply across socio-demographic as well as clinical contexts. Pharmacogenomic variant results should be incorporated into the EHR to better facilitate clinical decision-making at the initial point of care as well as far into the future. And once results are reported in the EHR, the group spent a long time discussing alerts that should be embedded within any clinical decision support system that signals changes to variant interpretation or changes to clinical standards of care as a result of evolving interpretation to treating clinicians, both immediately as well as in the future. And the combination of results as well as access to these clinical decision support tools should follow the child wherever and whenever they seek care at a healthcare institution. And this is really calling on EHR vendors and interoperability experts that can communicate these results across settings and across records. The ethical return of results must also be accompanied by workforce training. And so this point addressed the education need around variant interpretation of pharmacogenomic findings among clinicians, in particular pharmacists, genetic counselors, and others. And we agreed that rigorous evaluation and continued demonstration of clinical utility is foundational to the appropriate actionability. And therefore recommend that the return of results policies be based on a realistic evaluation of clinical utility as it evolves over time. And this is a call to action for the research community to conduct this work. And finally, if routine reporting is offered as a standard of care, it should be embedded in a comprehensive program that includes quality assurance, performance monitoring, and professional education as a point of collating all of these policy points together. And so our white paper has recently been revised and resubmitted to a peer-reviewed journal for publication. So we're really excited that this is the culmination of many years of work, and we hope to share that document with the rest of the GA4GH community shortly, and maybe by the end of this year. So I'll leave you with some contact information for all your critical feedback for Jan Friedman here, and I'm happy to take complimentary comments at the moment.
Thank you, Vaso. All right, one question from Heidi regarding the recommendation for labs to share aggregate allele frequencies by ancestry. Were there suggested databases to submit to?
Yeah, not yet, but I think we need them. I think we need them, and you'll find, if the points sound very vague and maybe sound somewhat general, it's because it was really difficult to reach consensus on some of these really contentious points. I think the choice of database is one, and there's a lot of difference of opinion in the group as to the security and data privacy risks. Do children preserve the right to the right to delete or the right to be forgotten in databases when they reach an age of majority to make those decisions? I think these are ongoing issues of ethical import for sure, and I think some of our general or statements really reflect kind of that lack of consensus.
So just to add on to that, do you think that the group is going to continue sort of meeting and tackling those challenges, or what are the next steps?
I think if Jan Friedman had his way, for sure.
For sure.
Yes.
We can help with that. Have you seen EHR vendors or health systems engaged with the work? Do they have any feedback for you? Are they interested?
No, and we need them also. So we are really welcoming that stakeholder group. I've found, at the start of our own group's formation, we didn't have recommendation from that stakeholder, or we didn't have participation from that stakeholder community, but I think certainly the implementation of these points or the uptake among healthcare systems and providers, they're a necessary community to bring on.
Great, thank you so much, Vaso. It's great work. Thanks. And with that, I believe we are done with this session. Thank you to all of our speakers. We now have a break from 5:30 to 6:30 where you can just go and relax. There are not any snacks out there because we will be setting up for a reception from 6:30 to 8 where you will be able to have snacks and drinks. So thank you. See you all later. Sorry, if I said snacks, I meant dinner. There will be dinner for you to eat during the reception.